Well, hello everyone. Welcome back to Adrian's Digital Basement 2. Today's video, we're going to be taking a look at this motherboard. This is a 386SX motherboard, and it says SCAT 386SX on it. I think that stands for Single Chip AT, and that's because the entire motherboard has, well, the entire chipset of the motherboard, that is, has been reduced to a single large chip here. I found this motherboard in a box of random junk. It had some battery leakage on it, or it has some battery leakage on it, so that might have caused some damage. It also looks like it has some broken SIM sockets, and the keyboard connector looks like it's pretty corroded. So what I want to do is plug this in, see if this thing even comes to life or works at all, and if it does, then perhaps replace some of the components that are broken, like the SIM sockets, and if it doesn't, maybe we can effect a little repair on it. I don't know. It's a second channel video, so I won't get too in-depth with the troubleshooting techniques and stuff like that. So hopefully this motherboard just works, but I haven't done anything to it other than give it a wash because it was absolutely filthy when I found it in the box. So let's take a closer look at it. All right, so this is it. So the single chip AT or SCAT motherboard, it's Chipset Technologies. There's the large single chip. It's funny that it calls itself the single chip AT because it obviously, besides the processor and the main chipset IC, there are a bunch of other support ICs, but I think they're mostly just things like bus drivers or bus transceivers that isolate stuff like the RAM or the ISA slots from the main chipset and the CPU. Don't even know if they're 100% necessary, but they're there. So it's funny, it's not really a single chip. Oh, of course you have the BIOS chip and the keyboard BIOS as well. And this particular motherboard, as you can notice, has a chip here that's obviously handling some of this multi-IO functionality. So floppy, and is that IDE? Yeah, that is IDE. So it has IDE and a floppy and a parallel port and two serial ports. Kind of unusual, to be honest, for something like a 386SX motherboard. It really wasn't until, I'd say, 486 boards where they started adding, or motherboard manufacturers started adding a bunch of ports to it, and then really this became 100% common practice on Pentium motherboards. I'm not sure I've seen any Pentium motherboard that didn't have a multi-IO functionality built on. It's kind of cool in a way to see a 386SX motherboard that looks like, what is the date on here? Looks like 1991. So I'd say that this board is from then, 91 22nd week. I'm just looking at some of the ICs here, 91 18th week. So we can pretty much assume this thing is from 1991. And yeah, to have the built-in multi-IO in a standard clone style motherboard, well, clone as in it would go into any AT case, it's kind of cool. Now you might be noticing on the bench here I have another motherboard, and the reason why is this is that 286 motherboard. Let's move this out of the way so the camera doesn't focus on it. This is that 286 motherboard that I featured, I think, on a main channel video where I overclocked it and I replaced the SIP sockets with SIM sockets. And it was these SIM sockets right here, which might be the ones that I need to replace the broken ones on here. I didn't even show the broken one on here, but bank 0 here. Notice that that's broken there. That clip is gone entirely. They're fine on that side. Bank 1 is fine. Bank 2 looks fine, and bank 3 looks fine. It's really just bank 0 that's damaged there. But it does look like if this motherboard does work, then this SIM socket, which has metal clips, by the way, so better quality, that should be a direct drop-in replacement. Anyhow, this 286 motherboard has also a SCAT motherboard or single chip AT. It's from Chipset Technology, just like the main chip that's on here is a different single chip. Even though some chipsets for 386SXs also work on 286s, these are two different parts. What we'll have to do on the 386SX, if it works, is look up datasheet for this chip just to see some of the capabilities of this board. I'm not sure the manual is available for this, but we'll talk about that a little bit more in a second. Anyhow, this 286 board, I really like this thing because I overclocked this slightly to like 14 point something megahertz, and at 0 weight states, this motherboard is quite speedy. In Speed 600, we get a speed around 21 megahertz, if I recall, and it's just a overall robust and good little motherboard. So I have it all hooked up to the bench power supply. Let's turn this thing on, and we'll just take a look at a couple quick benchmarks. So chip SCAT BIOS 1.3 decompilation or disassembly prohibited. Prohibited, you hear that? Prohibited. All right, so what's cool about the 286 board, which is what we're booting here, it has 8 megs of RAM, which is the max that this thing supports. The chipset does support 16 megs, but you need some additional support circuitry on the motherboard to do some multiplexing, and it doesn't have those chips. And it's not booting right now, and I wonder why. I think I'm just gonna jiggle the cards on here, and we'll try that one more time. Anyhow, oh, look at that, by the way, a little bit of rainbow action on the Orchid video card that I have there. That's the initialization of the ROM on the VGA card. Anyhow, it's maxed out with the RAM, and what's cool about this particular chipset on the 286 is it supports shadowing, so it can copy the contents of your ROM, which is slow, into the RAM, which is much faster. There it is, moving system BIOS to shadow RAM. And XT RAM test, by the way, wow, what's happening here? This was all working last night. Why is it freezing? It's not detecting my compact flash card, which is right here on this adapter. Just to make sure everything is plugged in correctly. So I have this small card inserted, and I know I've talked about this before, but this little card here has an XT IDE ROM on it, but it also has my RAM check ROM on there. They're both on there. I'm just gonna take out the postcard and we'll just move this into that slot. Sometimes what can happen on these clone motherboards I've found is some cards don't work super well in certain slots. Like there's some signal integrity issues, something like that, that can cause issues. So I have a normal compact flash to ID adapter there. Like I said, I had this working last night because I kind of just did a quick test just to make sure I had a good set of peripherals here. So the ROM card's obviously working. Yeah, it's not detecting the compact flash card. All right, stand by. I'm gonna try to figure out what happened here. Okay, it booted. What did I change? Well, I took out the the IDE and floppy drive controller that I have been using many years. I'm sure you've seen this on multiple videos. I have this sort of modified, so I have a couple LEDs on here to let me know that the floppy drive and the IDE interface is going, plus it can power up the XT IDE direct, or the compact flash adapter directly. And you'll notice I just grabbed a random one that I have. Actually, this is one that I found also in a box that has no backplate, so this is kind of perfect for testing and stuff. And I just moved the compact flash adapter over that was plugged into here, and it just freaking worked. Just want to do one last check to make sure it's still working with this card, and I'll switch back to this yellow card just to see. I just want to see it work. It's kind of why I had this on the bench, to be honest, to talk about the fact that it was also a SCAT BIOS machine, but I really wanted to see that all the hardware that I was using was going to work properly, at least with this. So that means with a 36SX board that it should also work. Okay, Inno disk, yep, 4 gigabytes. That is correct. Starting MS-DOS, all right. Yep, there we go, booting up fine. So I'm gonna pop out this green card and we'll go back to this one and we'll get this plugged in. Now I did install a right angle pin header just because I like it better when the card sticks, or this compact flash sticks up. Noticing this socket here looks a little kind of damaged. This is the one I changed. This motherboard had a broken slot. It was cracked over here. So I actually replaced that entire slot. I took it off another motherboard entirely. Okay, I'll just try it with the external power first. You probably clicked on the thumbnail for this video thinking you were gonna watch a video on working on a 36SX motherboard, but instead I'm sitting here flailing around trying to just get, you know, one of my working systems to boot. Look at that, it just freaking works now. You gotta be kidding me. This is so ridiculous. All right, so out with the power supply connector and in with the DuPont connector for the 5 volts, that is. Turn that on again. I mean, really? I guess what if there's a bad connection on this little DuPont cable? I suppose that could be the issue. These cables, the DuPont type cables, when they're good quality, there's no issues with those little slide-on connectors. But when they're the cheap replica ones, this one probably came from AliExpress or whatnot, they are definitely junk. Quality is not good, and they can often... Oh, right. And here's the funny thing. You see these LEDs here, that one and that one? Those won't work if I unplug this. See? There's no power anymore. So this thing is getting power, but maybe not enough? Oh, wow. I don't think the ground is necessary. I mean, the LEDs are lit up, obviously, so that's working. I mean, they're bright. Moving this around, I mean, yeah, hopefully you can see it. They're staying on solid, but my assumption is that it won't work again. Let's get the multimeter to the ready. I'm wondering, okay, now it works. Okay, well, it looks like we have a bad connection, I'm assuming, right? That's the only thing that can really explain the behavior. And I'm picking up 5 volts from this bus transceiver right there on that pin. That is actually soldered on, but this, right, okay, I think what I'm gonna do, forget all this silliness. I'm gonna cut this lead and I'm going to actually attach it to the side of the diode that faces me. I'm just gonna get rid of those diodes altogether. They're not doing anything, and if anything, the voltage that makes its way to the card is going to be potentially lower than it should be because of the diode drop. All right, there is the connection. Let's pull the card out. It's funny because these types of issues are some of the worst to diagnose because there are many potential faults that could cause this type of issue. And it's hard to know, is it a bad connection in an ISA slot? Is it the IDE card itself? The compact flash adapter, was it the power? I thought it was the power, but I guess it wasn't any of those things. The one thing that's been working constantly is the VGA card. I haven't had any issues. The video's always initialized. It's always working. Yeah, look, it's booting right up. All right, well, I figured out absolutely nothing. Absolutely nothing here. But let's get to the meat of this video and actually try to see if this motherboard is working here, the SCAT386. So let's look again at the battery leakage area. We definitely have some corrosion. Crusties are there. The via, that pin leg, see on the side of that package, it's got some crusties. There's some crusty there. Looks like the leakage definitely came down this edge. It may be hard to tell, but it's the connections, the solder joints are way shinier on these chips than on this bottom edge. Looks like that starts to get shiny, but I'd say that the leakage from the battery affected this area and this row of these ICs. This, which is almost certainly a clock chip, off the top of my head, doesn't seem familiar. We definitely have crusties here, or looks like a little corrosion. That looks okay. Oh, no, is that a little crusty there? Oh, no, we have a tiny bit of crusty there. Could be in there. I don't see crusties on the power connector, and it looks okay underneath the power connector, so that's good. Up here, I think that's okay. Is that a tiny bit of crusty right there on this, whatever this is, a fuse or something? Maybe, yeah, right there as well. So it made its way over here. Oh yeah, around the keyboard jack, crusties. And then notice the corrosion on the plating. It looks like some green crusties are inside of there as well. So on first blush, looks pretty good, this motherboard. You don't really see any issues. And the back looks completely unscathed. This was me removing the battery, the little flux there. But there's definitely some work to do on this edge. But I don't think it'll hurt to just try to power this up. We'll use the post card, the post analyzer. I want to see some signs of life on this computer first. Now, we don't have any RAM in here, so it's not going to work, but we should get postcodes. Here we go, 3, 2, 1. All right, great sign. Executing code. Right now, it's probably beeping about no RAM, so we can plug in the speaker. Let's try again. 3 beeps. Yeah, I'm gonna say that that's probably a RAM error of some type. Just for fun, I'll plug in the VGA card we were using. See if this makes a difference with the postcodes. No, we're still getting 6. And I'm gonna try to install a little bit of memory on this board. Even though those sockets are broken, I think it should be good enough for us to test with. They're held on with one side, but worst case, if I get them in the correct way, I can just hold them manually. Usually one clip is actually enough. All right, let's see what happens now. All right, I'd say it's posting. It's up to 61. Let's get the video connected and the keyboard into the crusty oh, it's very crusty. I'm gonna leave the keyboard unplugged for now. I think I'll just switch this keyboard jack if we're getting video. All right, it is posting indeed. Oh, same BIOS, SCAT SX BIOS though. Okay, cool. Right, it's only seeing 1 meg of RAM. That's weird. These are 4 meg sims. Yep, battery is dead. All right, well, that's great. This thing is showing signs of life, which is excellent. That means I think it's worth cleaning up the board a little bit. There's probably no bad connections due to bad traces or anything like that. I don't think anything has been eaten away to that extent. I think the extent of the damage on here is the corrosion in this keyboard jack, which probably would be fine with some cleaning, but I have a spare right here. I could just swap that out. The broken SIM socket, and then I need to just really scrub and try to get those crusties off of the board. So I do have a squeeze bottle here with vinegar. It's worn off. I'm going to use this to strategically apply the vinegar to the board. Oh, this connector needs to be swapped out as well. It's not looking so hot. Oh, come on, stay in focus, please. I'm not really seeing a lot of bubbling or anything, right? I'm just sniffing the bottle to make sure that it's really vinegar and not just water. And it is definitely vinegar. So what I'm going to do is I'm going to grab this little poker tool and I'm going to use this just to kind of dislodge the crusties that we see. And with the vinegar there, it helps. So this is a plastic tool, so it shouldn't scratch the board, at least not badly. So remember, we saw a little bit of the crusties on the edge of these chips here. See how the vinegar is running along the board? This is surely what happened with the leakage from the battery. It looks like it stopped here. See how shiny those are, but these are dull? So that definitely had the leakage there. And the leakage was, oh boy. Yeah, sorry about the focus issues. Leakage was definitely around here and definitely around this area as well. Oh yeah, there's some on that chip there. So again, the idea is here is I just want to try to, well, identify anywhere where there is some bad crusties and scratch them away. Oh, I got some bent pins here. Nothing that I can't easily fix. And then now I'm just going to use a brush just to really try to get in there. By the way, you can see here that the board is rated for 20 megahertz, but we have a 16 megahertz part and a 32 megahertz oscillator. So this thing is going to be running at 16 megahertz. Could try to swap this out. Sucks this is a smaller footprint. I don't have that many of these. Most of the crystals I have are this size, the larger size. I mean, it's functionally the same. They're just a different package. Actually, so a little bit of corrosion here. No. Ooh, it looks like we have a manufacturer under this socket. How weird is that? Yeah, I didn't see a manufacturer on here. SCAT36SX, something, let's say MFG Inc., like someone manufacturing. Yeah, it looks like that's probably manufacturing. But the name of the company, but it seems like the name of the company is right underneath the middle of that socket. How odd, what a strange place to put it. Why would they do that? Anyhow, it looks like the crusties have come off these chips. It's kind of what I wanted to see. And around this area, it looks pretty crusty free, good. Let me get it over here. I have a bunch of vinegar on this brush still. So I will note, if you're putting vinegar on a board like this, it's a very good idea after you're done to give the board a wash, at least in the whole area where you've applied the vinegar. You shouldn't really let it sit there. It is an acid. So theoretically over time, it could cause some issues. I tend to take it up to the sink and just soap and water clean the board. Just floppy connector here got a little bash. Who knows what happened to this board. Okay, I think what I want to do next, while this is sort of soaking with the vinegar, is remove the keyboard connector. But my desoldering iron has been a little clogged up seeming lately. Like it just doesn't work very well. I have a feeling I need to change this filter here. It could get very clogged up, sort of like a cigarette butt. Oh yeah, I think, see how it's sort of a yellowy color? Pretty sure that it's far gone. Oh yeah. Oh yeah, take a look at that. I got it's blocking up all the airflow. Got some spares in here. Probably should order more. If you have any good recommendations of spares for these pumps, other things I should be buying, let me know. I have to say, I swear by my little tip drill bit. That's a Hakko part as well, to clear out the tip on this thing. But these filters, I bought the real deal too. These are Hakko parts. Okay, that has been reinstalled. And I can hear it sucking through the end, so I think that's probably good. So I'm just going to put some fresh solder on these connections. Ooh, it's making all sorts of weird noises. And one of the joints is really crusty. Definitely got some corrosion on there. I'm going to apply some hot air to it while I do this. All right, so I have all the joints out for all of the pins, but it's super corroded along the edge here with the shielding. So you see it's flopping around. So I'm just gonna break it off and try to deal with those with this part out. There we go. Yeah, this little tab thing gets soldered down along this edge here, right here. So I just want to show, so this is what it looks like on the underside. See, those are the pins that were left behind, and it's such a mess. And look how terrible those vias are. So what I'm going to do is I'm going to use this with this little green pad on here just to sand this down a little bit. The hope is that I could expose some fresh pad that I can then solder more easily to it. Same thing on this side. A little IPA, clean this off. So that helped, using that green pad. Now I will need to make sure that these vias are connected to the traces that they go to, because you can have breaks right there, and see how it almost looks like there might be some breaks. This stuff over here doesn't matter as much. This is just ground, and it just helps solidify the keyboard connection into the board. But we do have to pay attention to these traces. At least on the back side, now that I use that little abrasion tool, that looks a whole lot better, at least on these contact pads. This, on the other hand, is still a bit of a disaster. So I really need to try to clear these little bits of tabs and things out. So I'm going to use the regular soldering iron here. And we will apply fresh solder and use some tweezers. Okay, I think it went down through the board. Okay, I tried to grab that and it disappeared. Let's try the next one. I'm gonna use this single tweezer, like broken in half thing. I'm gonna try to poke it down. I'm just not getting the heat transfer I expect, but I think that worked. Let's try this one. Okay, that's good. This one should be clear already. Okay, you can poke that through. This one, though, not so much. There we go. All All right, most of this pin is sticking through here. Okay, there it is, I grabbed it. All right, I can stick this through all those holes. So I assume they're clean. All right, they're clean. They're still really bad looking, but they're clean at least. Okay, let's see about these pins making their way to the appropriate place. So I'm going from the via on the far side. There. That's good. That one's fine. This one. That one's good as well. Yep, looks good. And I bet you this one is ground. I bet you this one is like 5 volts or ground. I wonder what this is. Could be one of these other ones is 5 volts. This one is 5 volts here going to L4. And that one is the ground right there. Okay, I guess that pin's not used, or on this board it's not used. There's no trace on this side. And there are no traces on the back side, so it's definitely not used. So this, which has those pins that go into those things I cleared, this should be a nice solid fit. There it is, perfect. All right, so I have one pin connected. I'm just squeezing the connector onto the board to make sure it's fully seated. And I have it resting up against this wire stripper. I'll do one of these pins here. Like that. Okay, good, the connector looks good. And this side needs a lot of heat. These are ground pins. That is one swapped keyboard connector. No more corrosion. Much, much, much better. Now what I don't love is that this little inductor here looks pretty crusty. Right there. Wow, these are the worst tweezers. Unimaginably bad. I'm just gonna scratch at that pad a little bit because I want to reflow it. I just want to get some of the corrosion off of it. That didn't really work. Where's my little mini Dremel here? This is a Jank Life? Jank Life? Gonna switch over to this. This is the engraving tool, which has a much finer point. I mean, I see silver and copper now, so it's better. It's definitely better. Yeah, I actually see something shiny on there. Now look at the trace. Goes here, makes its way, looks like to there. So I think it's, wait, which one is it? I think it's this top one. So it goes to this pin. Make sure I'm in continuity mode. I am. Yeah, okay, I'm touching the top and there's continuity. Plus this side should have it. And there is, yeah, because that's an inductor. So there's a little bit of a drop, but mostly goes right through. So that's a resistor pack pull-up or something. Hopefully, well, we'll find out. I mean, we haven't tested that the keyboard actually works. We'll know more once we actually power this thing up. Okay, so the vinegar has really soaked for a while. I need to get these pins out of the battery connector because I'll want to put a regular CR2032 in that position. So let's try to get, well, actually, you know what? Before I try to get that pin out, which absolutely looks horrible, let's do this to it. Oh yeah, look at that crust coming off there. You see that? Nasty. That makes it very difficult to add heat to this joint to get that out of there. Actually, that was just solder that was on there. Huh. Let's see here. Let's apply Okay, that actually flows. Wow, look at that. It's going to be the same on this side too. So we'll do the same thing. I think when I took the battery off, I was able to pull that pin out, but these ones, I had to metal fatigue the battery right out of the board because there was just no way I could get heat onto it. So I think there's pins that are left in there, in other words. Good thing is after you grind it away though, see I could actually get some fresh solder on there. Now I'm looking for my single tweezer. Not these junk ones. I bought these recently. ESD13. These are garbage. I'm throwing that in the trash. All right, here's this one. This is much better quality, even though it's broken in half. So what I'm doing is I'm just poking the hole to kind of push through whatever's in there, through to the other side, hopefully. It's not really working on this one. Oh, there we go. Oh yeah. I think that did the trick. See, those are the pins there. Yep, able to get those out now. This one is being stubborn. There we go. Might as well take off that pin header, since we know that's crustomatic. So that was this pin header. Oh, et voila. Look at that. What a mess. Yeah, part of me wonders if this chip is going to be permanently messed up or damaged. It looks pretty sad. Oh. Let's try to hit it with the polishing bit a little bit. I don't know if that actually helps at all. Probably not. All right, well, it looks a little bit better. Just a little bit better. I think what I'm gonna go do is I'll take this upstairs and I'll give this a good wash, get all that vinegar residue off the board. Then we'll see if it still works. And I'll need to, if it does, put a little bit of nail polish over these exposed traces that I've since exposed. I don't know what I did. I just rubbed the polishing tool over these chip legs and it seemed to have really done nothing. And then if the board still works, we can figure out how to get a CR2032 holder into this board, and we'll have to disable the charging circuit, which almost certainly is this little section right here with these diodes. So let me go upstairs and give this board a bit of a wash. All right, I washed the entire side of the motherboard over here where any of that vinegar was on the board. So that is all gone. It's looking pretty good. I did put a little bit of nail polish over those exposed traces. One thing I'm noticing is we have a couple extra jumper blocks that's unpopulated here, W1. And over here, or somewhere else on the board, where is it? Here it is, W3. So it implies there's a W2 jumper block somewhere on here as well. I'm wondering if I should clear these out and maybe we can do interesting things if we install jumpers on there. And let's see what it looks like on the bottom side here. Where are those pads? Here they are, there. Okay, so looks like one of them is already permanently jumpered. That's this one over on the right. I wouldn't be surprised. It is my assumption, because we have traces running off to stuff, that these two pins are ground. And we'll go here for ground. Yep, those are grounded. So I'm gonna break that trace there, and I'll clear these out, and then I'll install pins, and we just need to reinstall a jumper between those two pins. And now I'm curious what exactly this will do. So we'll use the engraving pen. So yeah, that is definitely broken now. So the jumper that was installed was the one closest to the serial ports. Giving the board a once over, looking for W2. There it is, W2. What is W2? It is permanently connected. So let's break that and install a header on there too. There we go. Now it's not connected. All right, W2 is installed, and that one was permanently jumpered, so we will re-jumper that. And the 4-pin block, the one that was permanently jumpered, was the one closest to the serial ports. So we'll jumper that as well. And then just for reference, W3, this one had 2 jumpers on it. It has 4 pins across, and that has 2 jumpers. And then there is also the battery connector, but I'm not going to reinstall that because I'm going to try to install one of these battery holders instead. Oh, that's backwards. So positive is this side, and it's marked positive on the board. Okay, there it is. It's installed. We'll just check to make sure the polarity is right once we power it up. It's going to try to charge this battery, which is not something we would want, right? Okay, well, it's time to test. Let's see, did I damage things? The RAM is still installed. Get the postcard installed. Now I can plug the keyboard in without fear of messing up that connector. Okay, let's plug in the speaker. I guess now I'm thinking about it, maybe this doesn't support 4 megabyte sims because we can only have 16 megabytes in the board, which would be 4 sims of the 4 meg variety. Maybe it only supports 1 meg. Here we go, 3, 2, 1, power on. We got postcodes. Do we have video? We would if we had the cable plugged in. There it is, system battery is dead. Of course it is, because it's not installed. F2 for setup. This looks just like the BIOS on the 286 board. Absolutely the same. So we don't need that. Date defaults 291. Yep, it's only showing 4 megs of RAM. This should have second pages. Page down, numlock on or off. Oh, wait states. We can control that right here. 0 wait states. Very nice. Shadow system BIOS. Yep, sure. Video enable. EMS. Okay. DMA clock source. Right. So lots of configuration options. Fancy. Okay. So just like the single chip AT or the SCAT chip on the 286, I'm pointing to it, but you can't see my finger. It allows for downclocking the system. So right now, CPU clock X1 is actually half of the oscillator that's on the board, so it's 16 megahertz. But you can do half of that, so we run it at 8 megahertz, 4 megahertz, or even 2 megahertz. Lets you turn off and on parity for the RAM. I think this is parity memory, but whatever. Dynamic memory sizing, okay. Oh, what does this let you do? So what are these RAM configurations here? Let's see here. Wait a second, unknown, that's funny. No system memory, okay. So 2 by 256, no, it thinks they're 1 megabytes on here right now. It thinks they're 2 by 1 megabyte. Okay, I don't remember what it counted up now I think about it. I think it was 640 plus 1 meg of extended, and then there's a shadow memory, so that is 2 megabytes. 4 megs, 6 megs, 8 megs, that would be fully populated with 1 meg sims. To go to these larger configs, you need the RAS encoders. So this is exactly like on the 286. To go above the 8 meg barrier, you actually need to have some extra circuitry, which I don't think this motherboard probably has on it. Yeah, because look, it's like 10 1 megabyte sims, 12 1 meg, 14, 16 1 meg sims. There's not 16 slots on here. So I don't think this thing actually supports, oh, 4 megs right there. Oh, I went right by it. Wait, come back. I can't go back there. It had 4 megabytes, didn't it? Oh, 16 megs, 4 by 4 megs. Well, I only have 2 of those modules installed. Let's leave it like that. Let's just see what happens. So what the other motherboard has that this doesn't is the other one allowed you to actually adjust the registers directly. And all of these settings translate into various register settings inside the chip. This one right here, the chips and technology chip. Doesn't seem there's a way to get to that. So I don't see something to get into the registers. Unless I'm missing it. No. Okay, well that's interesting. F10. At least the keyboard works. Oh, how funny. It's showing us the postcode. So it says 6 on screen, and that's the same as the postcard. I wonder if that's complaining because it is looking for 4 megs of RAM or 4 4-megabyte memory modules and it can't find it. I'm gonna grab a couple more. So these are 4 meg modules. I write 4 on them just to kind of help me realize that. You know what's not good about this configuration is the ISA slots can conflict. Oh, these slots really hold on to the cards. It can conflict with the memory modules. Okay, there's 16 megs. Yeah, this card here actually doesn't conflict. Wow, that's neat. Well, I guess it depends on what card you have, but this card will work because if I push it down, it actually goes between the memory modules right there. And there's nothing on the card that sticks out that would hit the memory module. That's clever. Good design on their part to space these out a little bit. All right, let's see, does this thing work now? Yeah, it's posting. So do we have 16 megs of memory now? It doesn't support 32. You can't go that high on 36SX. Only supports up to 16 megs. That did not work, did it? It still thinks it's 4 megabytes. Control-Alt-S. Let's just check that. It's still set that way. I wonder if there's a jumper. I wonder if one of the jumpers allows us to do this. F10. And there it says 6. All right, well, for now, I guess I should just try to boot the system at least. Let's take off this jumper by the math coprocessor. I'm just curious what this one does. This is one of the ones I added. It is my assumption that the dip switches here are it's going to do 4 megs, I bet. Yeah. Memory size doesn't match. Boot failure. Yeah, whatever. Let's turn this off. Let's take this jumper off over here. Okay, right away, that just caused it to fail. Oh, that was a one-time problem. That was odd. All right, same problem. I'm going to take these jumpers off over here. These are the ones closer to the RAM. I'm just going to put both of them off. Let's see if that... I just want to know if it could maybe address... That's weird how it's not happy addressing this much RAM. I just want to know if these jumpers maybe allow it to have 16 megs. We'll have to go see if there's a manual around for this board. Nope. Extra CMOS checksum is bad now. Okay. What is it unhappy about? F2 setup. Do we lose our settings? No, it's still... Oh, I should maybe turn off this. Okay, let's try that actually. F10. And let's put these jumpers back. So all the jumpers are back how they were originally. It's posting. Now it's showing 512K. I have a thought. Could it be... No, it couldn't be. I was going to say, could it be that 1 sim per bank? That couldn't possibly be a way that it works. No. Oh, I lost that top-down camera. Ran out of battery. I'm just going to install the IDE card that you can't see me because the battery died. It's charging now that the camera's off, and I'm putting in the ROM card as well. Okay, here we go. F1 to continue. Okay, it's going to boot, I think. Maybe. Oh yeah, look at that, it actually worked. I held down shift. Let's see how fast this thing is. 16 megahertz is what I'm quite sure that this runs at. 16 megahertz, indeed. Now the funny thing is, I'll unplug the speaker here. The interesting thing, I'm quite sure that 286 board running at 14 and a bit megahertz has a speed benchmark in here of around 21 megahertz. So barely different. I'm not 100% convinced this thing's actually running at 0 wait states, even though I think that's how it's set in the BIOS. Let's reboot and take a look. Yeah, 0 wait states is enabled. So if I change that to 1, let's see what else is in here. Bus clock, refresh command. This has to do with how often it refreshes the DRAM. I think the smaller number, so 140 nanoseconds, it means it refreshes every 140 versus 210, which is what it was set to, and 280 350 nanoseconds, it refreshes the RAM less often, which actually gives you a bit better performance. But I don't remember what it was set to. 280 was the default. I'm going to leave that alone, but I'm going to go back here and change this to 1 wait states, and let's hit F10. Let's see what that does in Speed 600, if that slows down the CPU. If there's no change, then I'm going to wager that this setting in the BIOS doesn't actually do anything, and maybe there's one of these switches that does that, or jumpers. Let's see. Let's let this boot up. I'm going to have to hit F1 because it's still unhappy about the RAM size. Oops, I noticed the video card speed was not that great. Oops, keep typing wrong. I noticed the video card speed wasn't great. Oh, it did make a difference. Okay, so it is running, I guess, in 0 wait state mode. And yeah, as the video speed is only 3000, that's pretty slow. But I think this video card that I have in here is just not that fast. Like, there's a big difference between one card to another. Some cards, video cards that is, run in 0 wait state, some run in 1. This must be a 1 wait state card. Seng Labs cards like this, ET4000s, I think that's what this is, should run around 5000, 5500 on ISA like this. Just depends on the speed of the ISA bus though. So going back into here and changing this to 0, and let's change this to 350. Let's see if we get a little bit better performance now out of this particular motherboard. There should be a slight improvement over the 280, and that's just because every time the DRAM is refreshed, it kind of halts the CPU, and the CPU has to sit there and wait a little bit, which wastes time and slows things down. Well, I'm realizing now that it's interesting that it's even booting, because there's an IDE port on the motherboard. I didn't even think about that. I wonder if it's currently configured for that to be disabled. Otherwise, there's a bus conflict between the yellow ISA card I have in here and what's on the motherboard. 21.84? I think that is slightly faster. Wasn't it 20 point something last time? I didn't note that. I'll check in editing to see if there's a speed improvement here on the CPU speed. All right, so Jim Leonard's top bench. We are matched performance, well, 34, slightly slower than a Dell 316SX. Which is a system that runs also at 16 megahertz with a Paradise VGA card. Now, Jim Leonard's top bench here, it takes into account not just the CPU speed, but also the video card speed. So if you have a very slow video card, that can dramatically affect the benchmark result that you're getting. So my VidMem speed is 336, kind of moving around a little bit. And on Jim's test results down below, Trickster was Jim Leonard, 391, so slower. And the opcode speed, though, on his system was faster, and the mem speed was also faster, and mem test was roughly the same. So that accounts for the slight difference there, is because his CPU actually seemed to be running a little bit faster than mine, than this one at least, but the video speed is slower on that Paradise card than this one, but the total is actually a little bit faster on mine. Oh, I'm sorry, a lower speed or lower number of score is actually better. So yeah, his CPU is a little bit faster, video speed a little bit slower. My video speed's faster, my CPU speed is slower, but then my total score is better because it adds that stuff all together. All right, so let's dump the ROMs, because I think these ROMs are not available. This particular Chips and Technology ROM is not available. There's a SCAT directory there. That was from the 286 board, but we're gonna go into the SCAT 386 directory, and we're gonna run ROM dumper, which is something that Jim Leonard also wrote. And this will dump all the ROMs that are found, which are gonna be the XT IDE ROMs, plus I think my memory test ROM that's on here, but really the ones we care about are the F000 through the top of memory space. That's the 64K of the ROM BIOS that's actually on the motherboard. So we'll just delete those. And we're left with those files right there, which are actually the ROM BIOS on this motherboard. So that's perfect. I can concatenate those together into a single file and then upload that to, say, the folks who manage the RetroWeb. Speaking of that, let's try to search for this motherboard. So yeah, there it is, SCAT386, ATWR Rev C. Well, that's the motherboard. That's definitely the motherboard. But this one has an AMI BIOS on it. It also has better SIM sockets that have metal clips in them. I'm not a fan of this image viewer thing that's on here. They look like metal clips, so yep, slightly better. there are jumpers. Oh, it's labeled on the motherboard, which is not on this one. So it looks like you have them installed, pin 1 and 2 and 3 and 4, which is how it is here for 1 meg or 256, or you remove them and you just have 2 and 3 installed, which would be these two, for 4 meg. All right, well, that's what we need to do. Ah, so this has made in USA on it. This one I have in front of me doesn't say that. It looks like there is writing under the Mathco processor, just like this one though. Let's keep looking around. Does this have like evidence of leakage on it? Yeah, it looks like it does, a little bit. Not as bad as mine. There's W1, not populated. And I didn't look at W2, not populated as well, so I have since populated those. But yeah, AMI BIOS. Okay, very interesting. There's the artwork, Rev C. And I know you can't see this because the camera ran out of battery, but this says artwork Rev A. Now I wonder if the difference is just the silkscreen artwork, or is there more to it with the traces and stuff like that? So why don't we change this to be 2.3 for the 4 megabyte memory modules and see what that does. Okay, I have changed the jumpers. I know you couldn't see me do it because the camera is still charging up. Let's see what that does. See if we get the full 16 megabytes of memory. Nope. Oh, I realized I set it for 3.4, not 2 and 3. So that's my bad. So I'm going to reconfigure this for 2 and 3 as it was marked on the silk screen on that picture. There we go. That's it. It's counting. It's going to have 16 megs. That is freaking awesome. Thank you for whoever uploaded that picture to RetroWeb. Right, so that absolutely worked, which is very cool. I'm assuming we can change this to enabled and then hit F10. Okay, very cool. Now I'm still curious about the fact that the floppy controller and XDID I have plugged into the ISA slot are working, even though the onboard stuff is theoretically enabled still. Chips and technology, 82836, single chip 36SX, SCAT SX. That's the name of the chipset. Max RAM size, 16 megabytes. Parallel, serial, IDE floppy, just like we thought. Known issues, yep, leaky battery. Is there a manual? No documents available. I'm curious, if we look and check it, are we gonna see serial ports? Yeah, parallel ports and serial ports. So the onboard peripherals are working. I guess there's a bus conflict right now between my card and what's on the motherboard, and it's just somehow working. Now with those W1 jumpers I installed, I'm gonna remove the one jumper that I did put there because that's how it was, and I wanna see if those ports disappear. I'm wondering if one of those jumpers that I've now reinstalled is for, say, disabling the onboard peripherals. It's funny, I'm still getting memory size does not match. Wondering what's happening here. Why is that happening? Wait states. Oh, am I supposed to type this in? Am I supposed to set this stuff? Select the memory? Oh, such a primitive BIOS. It does this. This is probably the problem right here. I gotta set the extended memory exactly to match what BIOS found is. You have to sit here and just like go through all of the values. Oh, I guess I could have gone looped around. All right, 232. F10. Doesn't seem there's a way to skip the memory test, like hitting spacebar, escape. That doesn't do anything. I bet you the AMI BIOS on RetroWeb, maybe that lets you skip the test, because AMI typically does. Okay, yeah, we got no memory error, so that was my bad. I just forget about these old primitive BIOSes where you actually have to specifically set the amount of memory. Okay, finally booting up. All right, so we still do have parallel port, serial port. So removing this jumper, that did not do anything. Having this much RAM in here is a pain. I'm going to try to like change all the jumpers and the switches on here just to kind of figure out what they do. But rebooting with 16 megs of RAM where it sits here and checks it every time, that's a big pain. Okay, so I just set the other W2 jumper and it didn't change anything with the ports detected at least. I should probably see if there's any speed difference somehow, like if this goes into the chipset. Should be 21 megahertz. Oh, it's a bit slower. Maybe I didn't set the 340 on the that one setting. I wonder if setting these jumpers or changing them while the system is running does anything at all. Let's do that. That did nothing. Nope. So changing those jumpers, that's the W1 block, did nothing. Okay, so I just took off the jumper W2, the other one I installed, and it dropped. That's almost like a wait state setting. Let's put it back on. Yeah, that came back. So that's almost like forcing it to go into one wait state mode. I have a feeling that's exactly what that's doing. Oh, I just realized something. What about the turbo jumper? Turbo switch. Turbo switch, there it is. Oh, no, that slowed it down. Okay, so the default with turbo is when the jumper's not installed, it's running in the fast speed. Now, if I take off the W2 jumper by the math coprocessor, it goes down to 8 megahertz. I assume that's one wait state or 0 wait states. Okay, so take off the turbo jumper and it has sped up. That can speed up the ISA bus here. That will speed up the ISA bus. And this obviously speeds up the DMA clock speed as well. But let's put this to /4. I guess reserved is some setting that it's not valid or whatever. CPU, we don't want to slow that down. Parity doesn't matter. And this stuff doesn't matter. Base RAM above 256 should be recognized. Why would you not want that? That's odd. So looking at the picture on RetroWeb, open. So it's set the exact same way here in the picture as it is on the actual motherboard. And the clocks, that's a 24 on my motherboard as well. Yeah, 32. Okay, it's 32 on the picture and it's 32 on my motherboard as well. And that's 14 point whatever, that's the same, yep. Okay. And looking at the dates, by the way, on these chips, 40th week, looks like it's slightly newer. 41st week. And this motherboard is like, this chip here is 91 17th week. So it does seem like things are slightly older on the one I have here. And yeah, it says Artwork Rev A on the motherboard I'm working on. And speed 600. Oh, now we're back to 21.8084 or 21.84. And this video speed sped up a little bit. It's 3700 now. So changing that clock divider did work. That sped up the ISA bus ever so slightly. I have a feeling it's probably the crystal oscillator 32 megahertz, the one that's normally divided by 2 to go to the CPU. It's probably that. And it originally was divided by 5, but now we're divided by 4, which obviously means 8 megahertz, which is the stock speed for the ISA bus, versus /5. So that would be a bit under 8 megahertz. Okay, camera's working here. Question is, if I pull this out and I take this compact flash adapter from this card, let's see, does this have a pin? Oh, I can't plug this in. I'd have to cut a pin off on the header. I think if I maybe plug this hard drive in, what is this thing, 8 gigabytes? I really want to see if the motherboard is configured for IDE devices. And we are causing a bus conflict by plugging in the card at the same time. So we'll plug the power into that hard drive. Let's see if this detects it now. This card should be able to detect the 8 gig drive without an issue. Okay, F1 to bypass. Let's let it detect the hard drive. Aha, it is detected. So I was causing a bus conflict by having both the IDE card there and the motherboard stuff simultaneously, which I don't love the idea of. Kind of what I need to do is figure out what switch settings disable the onboard stuff. So I'm just gonna willy-nilly just change those dip switches. I know the photograph, that was on RetroWeb is the way it was configured on here. So I need to switch it back. So I just changed 2 of the switches, the top 2 switches, to the other setting. I just want to see if it can't detect the hard drive anymore. So I'm going to go and just manipulate those switch settings and keep switching them until the hard drive is not detected. I guess I'll plug a floppy drive in, just make sure that they're not detected. I don't really want to use, well, I suppose what I could do is extra checksum bad. Okay, weird. Could be because the battery's missing, I suppose. I think what I'll do is I will write down, no, it's still detecting it. So I'll write down what I think the switches do and the jumpers that are on the board, and then the extra ones that I added, and I'll upload those to RetroWeb so that in the future, if anyone has this motherboard, they'll know at least what these various jumpers do. Okay, we're back, and I figured out some stuff, and it's not good, unfortunately. It's not good. Let's first go over my notes of what I figured out what the jumpers do, just so I have we have a record of that. So W1, this has 2 functions. Both of them have to do with the disk drive, and they go to the multi-IO chip here. So the B side, B right here, when the jumper is on, this has to do with pre-compensation for the floppy drives. The on is the default configuration, and that grounds that pin. One of the pins right there is grounded. That has the pre-compensation for floppy drives as normal, whatever that means. If you take the jumper off, which pulls up to 5 volts, that makes it this alternate mode. And then the other jumper, the A side there, this has to do with drive type. And the default configuration is the jumper removed, and it means the drive is single speed mode. And when it talk about drive, we're talking about 5¼ inch drives, and they run on PCs. If you have a high density version, a high density drive, they run at 360 RPM all the time, whether you're reading double density or single density. If you set it to on though, it allows this thing to operate in a double speed or dual speed spindle mode, which sends a signal to the drive if you have the right kind of drive. He's turning on, darn it. That's annoying. So back to what I was saying, when the jumper's on, yeah, it's expecting a dual speed drive. That means the spindle will run at 360 RPM when the double density discs are being read, and it reads at 300 RPM with double density discs and 360 RPM with high density discs. So that's all this does. And then W2, I didn't look too much further into. That was this jumper right here. That has to do seemingly with 1 wait state mode or 0 wait state. I think when you take the jumper off, it forces the chipset to operate in 1 wait state mode, irrespective of how the BIOS is configured. Then we have W3, which we already kind of figured out. That's this set of jumpers right here. It's got 4 pins. When all 4 pins are connected together with 1, 2, and 3, 4, that's 256K or 1 megabyte SIMs. And when the jumper is in the middle, like it is here, then that means you have 4 megabyte modules installed. Next up are the switches. I thought the switches, which are here, had to do with configuration stuff for this, but it doesn't. It looks like switch 1 has to do with the battery. So if you have an extra or an iCAD battery here, it goes directly through the switch on switch 1, and you can essentially turn it off. So it disables charging, it disables the battery entirely. And then switch 2 seems to be, well, this is the circuit that's handling the battery stuff, and it seems like switch 2 sends the voltage from this circuit, including 5 volts while the system is running, but also the battery voltage, to this little IC right here on this pin. And I don't know what this is exactly. I think it's clock. It's related to the clock. Look, that's a crystal oscillator here, right? And it's going right to the chip. So clearly this has for timekeeping. It doesn't have enough pins though. So I don't know if it's hooked up with I2C or SPI to the main chipset. I don't know if it's holding the NVRAM as well, or if that's held inside of here. It's quite possible that this is actually just doing it all, and then there's an SPI type bus or something like that where it can store the non-volatile RAM in here. Now the main chip for multi-IO, this is a 82C711. This handles all the multi-IO, the IDE, floppy, parallel, and serial, and unfortunately this is not controllable. Well, correction, it is controllable, but that chip specifically, which I found the datasheet for, wasn't very easy to find, but I found it and uploaded it to archive.org, so it is easy to find now. When you read the datasheet, it is specifically designed for motherboard applications and BIOS control. So all of the functions of that chip, other than the drive type and the I think the precompensation everything else is controlled via registers. So the BIOS at boot time is supposed to set that thing up, whether it disables, enables floppy, hard drive, serial parallel, like changing the serial parallel ports as well, like where they exist in COM1, COM2, COM3, COM4, etc., etc. Right now, it's clearly not happening. This BIOS on this motherboard we saw didn't have any options for this chip, and it must just default the chip. In fact, when you look at the datasheet, it does have power on defaults, and that's exactly how this is configured, with everything turned on and at the normal COM, IO address, IRQs, all that kind of stuff. So it's sort of my assumption that this chips and technology BIOS that's on here was the BIOS paired with this SCAT SX chipset, this single chip AT chipset, that it didn't really, well, it wasn't programmed to expect this multi-IO chip on here. So I think what's going on is that, well, potentially that later version of this motherboard we saw on RetroWeb has an AMI BIOS, and maybe that BIOS actually has the ability to control the IO stuff, because there's just no way to do it from external settings on this jumper, which is nice. I mean, that's pretty cool, and to be honest, very forward thinking. But at the same time, kind of weird that it's on here, and yet the BIOS itself has no way to control it, so you can't even disable any of that stuff. That seems like a terrible design. Now there's another version of the chip, it's the 82C712 instead of 711. That chip is functionally the same, except it's designed to be used on ISA external multi-IO type cards like this, ones that would have serial parallel game port and floppy and IDE. And that chip is different in that it uses jumpers to configure everything. So that would be where you see these boards that have a bunch of jumpers on them. That is the version of this chip that supports the jumpers, different than this one. So with all that said, I thought, oh, maybe I can just flash the BIOS and we can use the AMI one that's from RetroWeb, and then I would be able to see if I could disable those ports. I mean, not that I really necessarily need to, but I would like to be able to, because honestly, like, I plug in these cards with my compact flash adapter. It's just easier. I'd like to be able to disable stuff on demand. But that's where I ran into a problem, and it has to do with the battery circuit. There's something wrong with the circuit on this motherboard. So if we take a look here, you can see that I've done some work. Obviously the battery's installed in there, and you can see there's a component right there, and I have a couple parts removed, little surface mount components have been removed from the board. There was some corrosion around here, so I couldn't quite figure out or get good contact with the multimeter on this. Let's zoom in a little bit, and let me explain the circuit here. So the external battery, the pins that were there, this is the positive side, that went to this diode, D3, and that was connected to D2. So there were two diodes in a row. These are just standard 0.6 volt style diodes. I think they did that because people would hook a 6 volt alkaline type battery, four of those batteries up to this, so it would be more than 5 volts. So with a 1.2 volt drop, you're gonna get that 6 volts down to a reasonable level, right, before it gets to this point right here. This pad of D2 is connected to this pad on D1, there's D1. And that pad also is connected down this trace through this switch to this battery. The original battery connection went through these positive pins to the switch 1 and came out to that pad of this diode. The output of the diode, which is that side, goes into that via, which makes its way to this switch, and that switch then makes its way to this pin on this clock timekeeping NVRAM, whatever's happening here. So in a way, you could turn this thing, or you could set this switch like that to completely cut this battery off, but that would really only affect the charging and the operation of that battery. I think you would do that if you were going to use an external battery, just so you didn't have both batteries connected and you weren't charging this one anymore, especially if it was dead or whatnot. So what I tried doing is actually just routing this battery through the circuit as normal, right? Just connecting it, just putting just having it all connected, having the switches enabled, so the battery voltage would end up here, it would go through the diode, it would go to the chip. Well, the voltage seemed really, really low when I did that. I thought, oh, that's kind of weird, something strange is going on. Well, when this battery was installed there as just the default of the board without modifying anything, you'd get a 0.6 volt drop through this diode before it got to this chip. And I thought, oh, that's kind of strange. And the system would tell me that it had dead battery, like it wouldn't keep the settings. So I thought, fine, maybe there's too much voltage drop. So I removed these two regular diodes, and this part right there is a Schottky, and it's actually connected on the bottom side from this pin over to the positive of the CR2032. And because I didn't want this to get charged, because there's 5 volts available on these pins when the system is powered up, what I did is I cut this trace right there. So that's cut. So these pins, or the positive of the battery, is isolated, and this Schottky is connected on the underside between this positive on this external battery and here. And since I've removed these two diodes, this doesn't really do anything. And I had this like 0.2 volt drop, and I tried connecting it right to this location, and the system still wasn't working. And I'm not 100% sure what's going on with this cap and this resistor here. I don't know what those are doing, because that's this trace right here. So if I hook the battery voltage to that pin on D1, it goes to the switch, which was originally for going to this battery, but it goes to these parts as well. And this is not charging, because if I remove this resistor, there is still 5 volts here on both sides of this diode. It feels like I just can't see where the trace is going, the one that's going under the switches. It must go somewhere else and get charged from somewhere else. Well, here is the problem that we're getting. So let's get this. So we'll get that so you can see it. So right now this battery's around like 3.1 volts or something like that. And what I want to show you is that if I try to send the battery voltage through the Schottky to this chip, watch the current draw. 25 milliamps. That's what was happening. As soon as I connected the battery, it would start to drain very quick. And yeah, 25 milliamps is way too high of a current draw for a battery like this. You'd expect to have way under a milliamp of draw. And no matter where I hook this output of this Schottky up, I'm going to hook it up to the original location that's going through this diode. Well, I have the probes reversed. So if I do it this way, 12.2 milliamps. So it's less, but it's still too high. Yeah, if I go to this side of the diode, we get 25 milliamps. If I go to this side of the diode, 12 milliamps. Still way, way too high. So it drains the battery super quickly, and then it doesn't really keep time anyways. So there's absolutely, positively a fault in this circuit. There's no way that kind of current draw is normal. That's completely out of the realm of normal. I suppose what I could do is look around on these components. That diode has a normal diode drop, so that's fine. I can show you that this diode that's installed, I think I have the probes backwards. It's really hard to get good contact on things though, because everything is super corroded from the battery leakage. There we go, 0.6. Here's a transistor. It's not shorted. I don't know the footprint of this thing. 0.7. Looks okay. I don't immediately see any kind of shorts. I don't know what that transistor is doing. There's 2 transistors in a pair. Some resistors, capacitor. We have resistor, capacitor. That diode is okay. There's a capacitor. We have a cap here. There's another diode. Let's check this one. Looks super corroded. 2.7? What? Okay, that's weird. 2.7 volts. That's not, if I touch the leads together, you get 0. Oh yeah, there we go, 0.6. 2.7 was the other way, reverse bias. This diode's signal goes somewhere over there. Who knows? Some part of the board over there. But it's not shorted. So that's really my dilemma with this board, is we clearly have a fault somewhere in this circuit. I don't quite understand how the circuit is designed to work here. And it's probably because there's some low power stuff going on and it's trying to conserve power when the battery is running. Either way, even with this diode D1 removed, all 3 diodes removed, you still have 5 volts on both sides of this. This chip is going to get powered when the system is powered up, I suppose, as long as that switch is not set. If you set that switch the other position, then you don't even get 5 volts here, which presumably erases the the CMOS setting. But something was sending 5 volts to this pin of D1 to charge the battery. And this trace appears just to go right to here. And that trace seems to go right to this dip switch. But maybe, yeah, I don't know. Well, no, those are those traces there. I don't know. Without taking, I suppose the dip switch is off, but probably a whole bunch of components here, it'd be very difficult to reverse engineer this circuit to even try to figure out what's wrong here. And this is where people are probably going to be annoyed at me. This is a second channel video. I don't think I am going to do any further repair on this board at this point. It would take quite a lot of time and energy to remove all those components from this board, especially with all the corrosion that's on it, to then try to reverse engineer and figure out exactly how that whole charging circuit works, to then try to get to the bottom of what is causing that current draw. And it well could just be that non-volatile RAM chip has some kind of a fault. I suppose I could just socket it or remove it. Maybe I should do is let me quickly remove that chip from the board. And then what I'll do is then I'll check to see if we still have that really high current draw. And then if I don't, I know it's that chip or something associated to that chip, like something hanging off of that chip. Ah, well, that's curious. All right, so that is the pin that supplies the power. That's coming from there, right there. That pin, which goes through the switch, it goes to this location. And I think this cap, I mean, is that cap shorted? I didn't even check. Suppose, well, you know, when you have corrosion on the battery side, anything is possible. No, 3 mega ohm? That's fine. So battery voltage goes to there, through this diode, through this, through the switch 2, over to that pin. And then that is also hooked up, yeah, like I said, to this cap. I'm sure this is going to ground. Let me just check real quick. Yes, that is going to ground. Okay, so that's just a little bulk capacitance for this. Probably helps it stay alive, for instance. 22 microfarad at 16 volts looks like. Tantalum, those do short. Anyhow, but this trace also goes over here somewhere. If we follow it, goes to that via, and I bet you it makes its way to the main chipset. So that probably is for the non-volatile RAM. Let's see if I can quickly identify where that is. Okay, continuity mode. Oh, there it was. Yep, dead short right there. So that chip is being powered from the battery as well. Right, okay, well, let's put this little watch cell back in here. And let's see, what do we get? 12 milliamps there. Wow, 28 milliamps with that chip removed. That is wild. Now watch, if we set this switch like that, then there shouldn't be any current draw. Let's get that where you can see it. We go to the shot key here. See, it's basically nothing. Basically nothing. Yeah, basically nothing. Switch that. I don't get what's happening. Where did the current draw go? 1 milliamp. Am I not making good contact? Let's set that. Well, I'm totally confused now. Okay, what are we getting if we go here? What's happening? Where did the current draw go? You saw that it was there a second ago. Let's check the battery voltage. 2.9, so yeah, that current draw really brought the voltage down. This was a brand new battery. It was like 3.2 volts originally, but see how it's going back up again? What happened there? I don't get what's happening. Let's go to continuity mode and let's check what's happening here. Okay, so we don't have continuity. And now we do have continuity. So that setting there, when it's set to open, obviously that disconnects it. When we set it here, it is now closed and we have full continuity. So it's less than 1 milliamp now. So that high, 20 milliamp is gone. Now this is still too high. You can't draw a milliamp from one of these batteries and expect it to last any amount of time. And if we go to this side, 3 milliamps. But it's really supposed to be hooked up right there. Now I'm wondering if the current draw drops after a little while. It seems to be going up, if anything, not dropping. Of course, the thing is, the chip is missing, and clearly this chip's supposed to do something. I think what I'll do is I'll reinstall a socket in here. I have to make one, I think. I don't have a tiny one like that. All right, little miniature socket has been installed. We can push this little chip back in. And now we can see what kind of current draw we're going to get. If it goes back to, let's see if it goes back to what it was. No. I don't know. Let's just check it. Let's just double check that the switches are in the right setting. All right, so it should go from this side of the diode to here, and it is, and that's controlled by that switch, yep. Okay, so the diode is reconnected back where this battery originally should have gone. So for the positive side, so from here to there, 0.28, it's there, yeah, it's getting to that side of the diode. And then that pin, we got the diode drop of the Schottky plus this regular diode, so that's why it's 0.8. And then from here to the battery, what about to the chip itself? Yep, okay, so it's looking good. So that means if we put this in, there's no way to measure the current draw now. What we can do is take a look at the voltage on this pin to the chip. 2.918. And with the high current draw, it starts dropping. Oh, what was that? I mean, I'm not moving the probes around. Why did it? I think this is, yeah, look how quickly it's dropping. So whatever current draw wasn't there, it's obviously back. And it's completely killing this battery. It's completely killing the battery. Yep, okay, gotta get this out of there. It's just gonna kill another one of my batteries. Yeah, I don't know. I'm not sure what's going on. Okay, what I'm gonna do is use the bench power supply to provide battery power. So I'm gonna set it to 3 volts. Let's, I just hooked it up to the ground lead right there. Okay, 0.4 milliamps seems okay. Let's just let it sit for a second, see if this just suddenly starts to skyrocket. Well, I'm curious. I'm going to raise the voltage to 4 volts. Look, why did the draw go up so much? Okay, down to 3 volts, 3.0. Huh. How about 5 volts? 8 milliamps. So we're at 4 volts here. And just so you're wondering, I have the other probe there connected. See, it's on the milliamps setting. Sorry, this is in the way here. Okay. All right, we're at 4 volts. So if I go back to 3 volts, I don't know. It's just weird. I can't explain what's happening here. I just moved the probe out of the way to a ground point on the motherboard separately. So if we let this, I'll just stick that there. Let's grab another multimeter just so we can take a look to see what voltage we're actually getting at the clock chip. So it's getting just 2.3 volts, which might be too low. This might not even be enough voltage to run anything. And notice how the current draw is going up, it seems like. Let's put it up to 3.2 volts, 3.3 volts. Yeah, I mean, look how it jumped up to 1.2 milliamps. Let's see what we have voltage-wise. 2.4. I suppose what we can do is power up the board. Here, I'll stick this in here again, so it's, there we go. I'll plug in the power supply, and let's see what happens when we turn on the system. That should just drop to 0, obviously. Okay, here we go. Yeah, okay. Basically 0. So it's kind of what we expect. Turn off the system, turn off the power supply, that is. And that, I mean, this is off right now. And look how low the current draw is. Yeah, this is such a, this whole thing is just a bit of a mystery to me. This is what I would expect. That seems normal to me. Let's turn it off. That should drop to almost 0. Okay, turn it back on. Well, the thing is, I can assure you that I had the system plugged in with the battery, power it on, power it off, and then the battery started draining super fast, like 20 milliamps, as you saw. And I did this test where I'd power on the system, and then the drain would go away, and now the drain is gone. So I think all I can necessarily do at this point is I think I'm going to try to power up the system, set up some stuff in the CMOS settings, in the BIOS that is, and then see what happens. Now this is at 3.3 volts, by the way. We're getting this incredibly low current draw. I'm wondering if it's like, if it drops here to 3.0, no, it's still super low. Okay, I'm going to keep this at 3.0, which is a more typical voltage for one of these batteries. Let's turn the system on. That drops to nothing, which is expected. And let's grab the keyboard and let's try to watch what's happening here. All right, everything has been erased in here. So what I'm going to do is, okay, whatever, don't just set anything. I'm going to set this to 2025. It is January 13th. Okay, we'll save this. And I will power this off. I don't understand what's happening. I mean, I think I caught it on camera that the current draw was like 20 milliamps. And this is acceptable. That's normal. At that draw, a battery like this should last a decent amount of time. And I'm currently have the bench power supply. It's set for 3.0 volts. I don't know if that's enough to keep that chip happy, or whatever, the main chipset as well. I would imagine it is. I haven't run into this issue where a CR2032 with a Schottky going into the circuit was somehow not enough. Okay, well, I'm just gonna leave this here for 5 minutes. We need to give it enough time to drain the cap so it becomes unhappy that it's out of voltage. Why don't I just grab the other multimeter real quick? Let's just check real quick one more time. What are we getting on the chip? I mean, 2.8 volts? That seems really high. The reason why I think that sounds really high is we're getting 3 volts into the battery through this black probe, 0.2-ish volts drop, and yet there's another diode it's going through, and we should have an extra 0.6 before it gets to here. I don't know. It is interesting though that this seems to is going up. Well, now it's going down. I don't even know why this is fluctuating. Could be that this meter is just terrible. Okay, I'm going to stop the recording for a moment. I'm going to let this sit for like 5 or 10 minutes, get something to drink, and we'll come back and see what this is at. And I'm back. It's been about, well, 15 minutes or so. I was upstairs putting some dishes away, doing some things, came back down, and that's how it is. So yeah, this is what happened before. I had the battery in there hooked up just like this, seemed fine. Then it came back, turned on the computer. It said the battery had died. I checked the battery voltage. It was very low. And well, yeah, because 2032s, they don't appreciate this for any amount of time. So let's see what happens when we turn the computer on now. Okay, it instantly dropped. Let's see if it has forgotten all of its settings. Stop counting time or whatnot. I suppose what I can do, yeah, so battery is dead. Did not keep any of the settings, I don't think. Control-Alt-S or F2. I think I hit F1. Yeah, so it looks like the CMOS settings were not retained. Well, okay, so the time only advanced 4 minutes. It's 21:45 right now. So that didn't work. I had it set correctly to 30 minutes. Date's right. Settings are okay. I didn't change anything else. I wonder if it's the main chipset that holds the extra settings. This stuff, and this page is held maybe by the little clock chip. Not quite sure. But turning off the power to the system, that current draw did not come back right away. And I don't really know how long it took to happen. I wonder if I should remove this chip. It really, well, I don't know. I have an idea what we should do. I should let the current draw come back. And then instead of turning the system on, I should flip the switch, which shuts off the power to these two chips. Because I'm not 100% sure if the current draw is coming from something over here. There's the transistors and whatnot that are connected to power as well right now with the system off. Is this somehow related? I feel that's a no. I feel that those transistors are probably responsible for the 5 volts that is trying to charge this NiCad battery. And I can't imagine that this stuff here has anything to do with anything. Look how it's going up there. Just me sitting here talking. I suppose what we can do right now, since it's climbing relatively quickly too, I'm going to flip the switch. Pretty much all disappeared. There's a little bit of current draw, and then it came back. It kind of feels like, even when you have no battery, when the system is first turned off, it does retain the settings for a little while. So obviously with the capacitor here and whatnot, I presume that supplies enough power. Let's flip the switch again. Disappears. And that specifically cuts power to the chip and the chipset. All right, so I'm still at 3 volts from the power supply. What if I raise the voltage? I'm going to raise it by 0.1 volts. That did nothing. 0.2, so we're at 3.2, 3.3, 3.4. It is dropping. I wonder if it's some kind of a race condition when you give it too low a voltage. If I'm at 3.5 volts. It's climbing again. All right, I'm gonna go back to 3.0. I guess I'll go upstairs and put some more dishes away and work in the kitchen. I want this to get back to that 14 volts, and then what we can do is turn the power off and on, or raise the voltage a little bit, see if that exacerbates the issue. I suppose I could lower the voltage. Let me just do that real quick. 2.9, 2.7. I mean, it doesn't seem to really be changing, does it? So we'll go back to 3.0. There. Oh, did you see that? Went up to a milliamp there for a second. It's funny. So if I raise the, so we're at 3.4. Yeah, did you see that it went up to, it went up to like 1 point something, and it went back down. It's acting like it's charging something. Okay, so I'm at 3.0 steady state, and we're up to 1 milliamp here. So I guess it just climbs as the time goes on. So again, look, it's going quick now. Let's turn off the power. Let's turn the power off to those chips. Boom, it's gone. I mean, almost entirely. Turn it back on. Yeah, it came back right away. All right, so now the question is it this IC or is it the chipset? Because it seems to be one of those two things. Oops. I'm trying to find my chip puller. I think it's buried. The bench is a mess right now. I want to do this without knocking this probe out. Pull this chip out. Okay, well, it's obviously not that chip. Well, that's bad. That's bad. That is not good. We're at 3.0 volts, 2 milliamps. As far as I'm aware, the only thing hooked up right now is this. It's not warm or anything. I mean, it wouldn't be, not with 2 milliamps. All right, for kicks, I'm going to turn up the voltage to 4 volts. Right. So did you notice it went quite high for a moment, but then immediately dropped back down? I presume if I measure the voltage here, look, it's dropping. All right, let's cut the power. And I will install, look how there's that draw there though. I'll put this chip back in. Okay, that chip is back in. We're at 4.0 volts on the power supply. .2 milliamps. I'm just curious if the 3 volts from the battery is just not enough and the circuit gets into some kind of runaway, or I guess this chip gets into some kind of runaway or something I don't know about on here, and suddenly starts to draw a ton of power. Oh, this is gonna go to sleep. I went to sleep. Okay, there we go. Even when that's off, current can still pass because it uses a current shunt, so it's always connected here, well, through a fuse. Well, the current draw is still going up, and that's at 4.0 volts. But again, oh, look, it's quickly going up now. Ah, look at this. Look, it's like runaway. Absolute runaway. Look at that, just like where we were when I stepped away and came back. And it got there so quickly. So now I can try raising the voltage. Well, first let's try turning off the power here. Okay, so it's gone entirely. So it's absolutely like this chip. Well, we know it's not that chip. Or there's some circuitry or something on the board here that I just not, I don't know how it's designed. I suppose what I can do is I'll turn it off and we'll pop out this chip again. And then we'll turn it back on and see if it comes right back. Yep, okay. So nothing to do with this little chip. The battery leakage did not get to it. Is it entirely this? It's gotta be this. Well, okay, I'm gonna start raising the voltage, 0.1 volt increments. 3.1, 3.2, look at the current draw. 3.3, 3.4. What is the limit on this thing? 250 milliamps as it can go up to. Okay, so we're fine. So we're at 3.4 volts right now. And we'll get 23. There, it just changed scale. 25. So we're at 3.6 now. 3.7. 3.8. 3.9. 4 volts. 39 milliamps. This is outrageous. Oh, look. 4 volts. It's plummeting. It's plummeting. It still seems too high. We're at 4 volts. Now the NiCad battery that would have been on this board in place of the 2032 here, which by the way, would be hooked up in exactly the same spot. This is where the power would be fed in, exactly where the Schottky diode is. It's a 3.6 volt battery, but it is charged, well, with a resistor at 4 point something volts. But when you turn off the system, it'll very quickly get back down to 3.6 volts. And I guess there is the dropper, there's the Schottky diode, so let's measure what we're getting after the Schottky here. 3.7. So you would not get 3.7 for long. It would go away pretty quickly. Especially with this 2 milliamp. The battery is probably, I don't know, 100 milliamp hours. That means it would only last, even at this current draw, you wouldn't get very long out of it. Let me lower the voltage down a little bit. So now we're at 3.9, 3.8. And it's starting to go up quickly again. 3.7. I mean, look there. It's runaway. It's runaway. So now if we check the voltage after the Schottky, so this would be 3.15. That would be like what we were getting out of the NiCad. It would drain it so quickly. It would drain it in no time, and you would have a totally dead system. Okay, I'm going to go back up slowly. 3.8, 3.9, 4 volts, 40 milliamps. Is it going to like threshold and drop really quick? Yeah, there it goes very quickly. I mean, I still feel that that's way too high. I'm going to keep going up though. 4.0, 4.1, 4.2. Let's go to 4.3. Now if I measure this, we're probably going to have 4.1 volts after the Schottky. Yeah, 4.03. And we're down to 0.6 milliamps. It's still high. I think it should be like 0.06. Probably be more reasonable than that. That's just too much. There's also nothing to say that over time, because it seems to be creeping up, or maybe not. Just when I think it's creeping up, it goes back down again. So with everything we're seeing, I just feel that this circuit, there's something wrong. There's no way that it was designed this way, because the original NiCad battery, which was a 3.6 volt battery, there's no way that could have kept the settings for anything more than like a week at most, or less even. That doesn't make any sense. So something seemingly is wrong, and I feel like it's got to be in this chip, because if I lower the voltage back down, here we are to like 3.4 volts, skyrockets right away. 23 milliamps. And if I turn off the power that goes to the chip, because that chip is out, it'll be gone. There, 0.01 milliamps. And I feel that whatever this current draw is coming from these transistors, whatever this little circuit is here, that seems to be what is causing that. But this is not normal. And with that said, I don't know what could be causing this. I'm just flexing the board. Incidentally, this first switch has no effect anymore because I bypassed it with the Schottky. What about these other switches? Let's just flip these while this thing is sitting here. Yeah, no change at all. So the only one that has an effect on the battery are 1 and 2, 1 being the original battery connection, which I've bypassed, and 2 being power to these chips. I suppose the only thing that's still in circuit besides this is this cap right here, this tantalum. Maybe it's gone bad somehow. I don't know. I've never seen them do anything like this before. Let's take it off. I don't know. I don't know what else to try. All right, I removed that tantalum. Let's reconnect the bench power supply. No, that just immediately went up to 16 milliamps. Immediately, without that tantalum installed. Wait, what happened here? No. Did I lose connection? No. Well, that's strange. I'm at 3.4 volts. Huh. Okay, so I went back down to 3.0. Oh, no. There we go. There we go. That was just a glitch in the matrix there. 9.9, and we're at 3.0 volts. Let's go up to 3.4, which is where I was. Yep, there we go. Okay. That did not solve the problem with the tantalum, which is sitting right there. So that's the tantalum, that's the chip, 16 milliamps. Okay, so it wasn't a leaky cap. All right, look at this W2, the one that seemed like it was 0 weight states or 1 weight state. Lowers down. Is this like, is the battery voltage trying to power up this entire chip? It's kind of the only thing I can think that's happening right here. Why would that jumper have any effect? What about this RAM jumper over here? No. Well, that seems odd that has a dramatic effect. Now, the way this was installed, remember, W2 was already permanently jumpered on the bottom side. What if I push on this chip? I mean, that doesn't do anything. I mean, I kind of can't help to think that some voltage is like leaking through. Yeah, look, we got 1 volt on this jumper here. That doesn't make sense. That doesn't make sense at all. And we have 2.23 volts on this cap. 2.9 after the Schottky. And then 2.2. So there's some kind of a voltage drop happening over here in this part of the circuit before it even gets to this chip. Okay, what's weird is there's a little resistor R41 to 104. On one side of it, we have the 2.9, that's after the Schottky. The other side is 0.8. Is that where the current is coming from? That resistor? Well, taking it off didn't really... Well, it's dropping now, though. I thought it was dropping. It's not really dropping. Is it dropping? No, it's not dropping. We're still at 2.24 on the chip, so there's a bunch of drop happening, which I'm assuming is just this diode right here. So this resistor that I just took off, R41, it's connected to the same power source as the output of the Schottky. And then it goes to a cap, but I can't make out if there's another trace that comes out. Yeah, I think it bypasses the cap. I think it goes through the cap to that via, but I think it'll also, which is probably ground. It goes, looks like there's a trace there that goes to this diode, 5H, same diode as that one, 5H. And then it goes down, I assume, to this pad, which is a mess because of the flux. Unfortunately, my this meter is having range switch problems. Yeah, this is the new one I got too from Dave. It's like worse than my other one. Obviously works fine on these other ranges, but continuity, there we go. So battery Schottky goes, it's hard to see, but it's actually connected to D1, the pin on the left. I have it hooked up to the pad over here, but it makes its way there to D1, which goes to the switch, which goes through this diode to that via, through this over to here. But it also goes to this resistor to there. So that goes from here to there. It goes from there to this resistor, which goes to there, which is hard to tell where that goes. I thought it went to this pad on the tantalum, but that I think is hooked up to this and then to ground. Yep, there it is. So that is just sort of bulk capacitance for that. I don't know what this resistor cap, diode cap, which goes to ground, I think. Let's just check. Yep, goes to ground. And this one goes to ground. Yep, that goes to ground. But where does this resistor connect to? This must connect to something. Ah, it's this right here. Something up there somewhere. Okay. So R41 to this diode D5 goes to this R14, which then follows this trace somewhere up there. And that allows some of the battery voltage to make its way through this diode to something else. This is where having schematics would be extremely helpful. Does it go to that via there? Nope. This one? Nope. It's really hard to trace. It's one of these. Nope. Yeah, I don't know which one it is. And they're tented, so you have to really push through them. But that resistor was in place. It was working. It just had a lot of voltage drop across it. But that was not where the current draw was coming from, because I removed it and we still had a bunch of current draw. And we can test that. Going to milliamp mode. Yep, just immediately jumps up to 15 milliamps. And again, if we turn on the power, drops to nothing. Turn off the power, comes back with a vengeance even more. Turn on the power, turn off the power, with a vengeance. Let's go up to 4 volts, 30 milliamps, what? Let's turn this on, turn this off. What the hell, what? Let's pull the jumper. 25 milliamps. Just feels like the chipset is trying to run right now. Like it's trying to take the power from the battery and operate, fully operate. That doesn't make any sense. I really have no idea where to proceed with this. None at all. I feel like the problem exists in the chipset, and obviously not going to go replacing the chipset on this motherboard. This is not a special motherboard. It's just a 16 megahertz 36SX, but it's got faults. It's got some serious faults. You can ignore that. That's the jumper that I installed. This is the chipset here. The battery's up in this location there. This is where the battery is. You see the holder. So I don't know what that's doing over there. What is that under? The clock. Oh, must be something to do for the crystal. Yeah, that is on the crystal actually. That's the crystal oscillator. And I'm just looking to see, do we have any bad traces? Don't see anything. Oh, another bodge. Huh. What is that? That is the turbo light. That is the turbo LED. Oh, that's funny. Okay. Anyhow, I don't notice any problems. None at all. That's the other jumper pair that I did. That's a little bit of nothing. Got some scratches there, but they're not deep enough to cause an issue. I'm going to look at that with a a magnifying glass. I think that's just a blob of solder mask. I don't think that's actually a damage to the traces. I'm not seeing anything. These are some scratches here. But luckily they happen right where there's no, there are no traces. And a close-up look of the top side. Let's make sure none of the pins are bent, touching. They look fine. They look just fine. And you have to remember, this motherboard works perfectly when it's powered up. This problem only exists while it's in power off mode. There are no issues. None at all. Yeah, everything looks fine. This wasn't abused on the top side. Unless there's a ball, like a solder ball under there. That's possible, I suppose. I'm curious, is the power from this time chip, does it go to this cap here? Okay, yeah, it does. So that cap goes to that pin there. And then that side of the cap goes to ground. But yeah, this is the power from the battery, which is why I saw the battery voltage on that cap when I was looking. Let's see, is this, what do we have to 5 volts? Let's check 5 volts. 2.7 meg ohm to 5 volts. To ground, 2.7 meg as well. But obviously we're to the battery voltage, 0.2 ohms. That's not including the shock key and whatnot. And across this capacitor, 2.7 meg as well. Oh, look at this. This is interesting. This cap also has battery voltage on it. And so does that one. And so does that one. So these have battery voltage on them. I know you can't see the multimeter, but we're at 0.2. So does that make sense that this is getting battery voltage? I mean, we know that trace, it goes off of that pin, makes its way up here, I think to there. Yeah, I think it's, I think the battery goes to this pin there. You can actually test that. Yep, this is the battery voltage here to there. Yeah, 0.2 ohms. And then that makes its way right into the middle. This is the big chipset chip. Makes its way into the middle of that to these two vias. And of course I can't see where those go because it's right under the middle of the chip. Let's quickly check the data sheet. This is a long video. I hope people don't mind. This video is going to be like 1 billion hours long. Let's see here. One of these is going to have kind of what we need. Speaker, yeah, yes, we know it does everything. Show me the pinout. I need the pinout. VCC, I mean, this is what that's where it was connected. VCC and VSS. What? VCC and VSS. All right, checking the small clock chip I removed. It's this 17-stage oscillator driver. That does make sense. VDD, that's where the battery voltage was going. And yeah, the oscillator in and out definitely goes over to the little clock crystal. So this thing definitely needs to be powered up when the system is off, because this is handling the 32 kilohertz clock crystal for timekeeping. And then it must make its way over to the chipset. But then it seems like the chipset's being powered by the battery all the time, which doesn't make any sense, obviously. That should not be the case. Okay, so I know that switch 2 disables the oscillator for the clock. What happens if I turn on the system and I flip that switch, which I know cuts power to this pin and presumably the chipset as well? The system's not going to run anymore, right? So let's turn it on. Okay. The system is running. Let's flip the switch. No, it's still working. And if we check the voltage on the battery pin here, oh, we're still getting 4 volts. 4 volts? What about over here? 4.0 volts. That feels like that shouldn't be working. But if we flip that, this will probably have more like 5 volts on it. 4.8 now. I mean, how is the chipset running with 4.1 volts? That's clearly the VCC line. But it's working. All right, so if we go into the BIOS here, and I'm moving this around, if I remove this jumper, that does nothing. So that's with the switch off right now. And is the clock even running? No, the clock's not working right now, and that's because I have the little oscillator chip out. So yeah, you see that, how it's just sitting there doing nothing? Let's put the oscillator chip back in. See if the oscillator runs now. If we look at the data sheet for the chipset, I assume the oscillator output, whatever this chip generates, makes its way over to the chipset, and the chipset itself is what's doing the NVRAM and keeping time. Now that makes sense. And there it is, the clock is running now with this chip in there. So that chip is good. And that's not obviously causing the current draw. And that's with this switch 2 set to the open position, which I thought was CMOS reset, which it's clearly not. It doesn't matter how I have this set. It works either way. The only thing I can think of here is to look at the data sheet and try to ascertain what exactly or how it's supposed to operate when it's in power off state from the battery. What powers up the chipset to retain those settings? Yeah, that's the only thing I can think of to look up. It says right here, 146818 compatible real-time clock with 114 bytes of RAM. That is the part of it that is handling that. I looked at this before, but this doesn't show anything to do with power, at least that I see. Architectural overview. Internal config register 2G real-time clock, CMOS red. Okay, yeah, we know that already. Okay, now we're down into the pinout section. Can I figure out where is the power supposed to go in? Input. I'm looking for the power from the battery. Out. That's a numerical processor. It's obviously not memory. I/O channel. Nope, this is like bus stuff. Bidirectional, IRQ. Power good. This comes from the power supply. CPU reset. I'm looking at the clock ins and outs. We have the 14 megahertz oscillator. There's the CPU oscillator. There's the output that goes to the CPU, and there's the output that goes to the bus. Where's the clock? That's in the real-time clock. All right, I found this. PS diode for external real-time clock systems. Oh, here we go. Most applications require real-time clock to maintain active whenever the system is powered off. To accomplish this, the user must provide an alternate source of power to the 82C836. This alternate source of power is normally provided by connecting the battery to the VCC pin. What? A means should be provided for switching between system, power, and battery. A circuit such as the one shown in figure 3.3 may be used to eliminate power drain on battery when the system power is available. That's 3.2. Here, 3.3. Okay, battery, diode. That's totally what, this might be exactly what's on the board. Maybe I should have looked at this. So when you use the 6-volt battery external, it had 3 diodes in a row. And then what I did is I injected the Schottky diode output of the CR2032 right here before, I think, this one. What's this PS signal? Multifunction pin 5, multifunction pin 4. So that's where the oscillator goes into. That's the 32 kilohertz. And power good, that just goes directly here that's from the power supply. I wonder if this circuit here, this multifunction pin 5 PS signal, is this what tells the chipset that it needs to be running on backup power, not primary power. So to draw like really low current, this multifunction pin 5, that's the only thing I can think of. So obviously the VCC power supplies power to the chip normally when the power system is powered up. But then this here, which I kind of feel is that little tiny resistor that I took off. I think it was a 104. Isn't a 104 100K? I think it is. And it had a little cap. And it had an extra diode as well. But I wonder if this, when it detects like low voltage over the 100K, for instance, you know, like 0.3 volts or whatever, that tells this thing, hey, by the way, you operate in low power mode. Let's look up multifunction pin 5. Oh, let's see what it says here. Might talk about it. A similar precaution needed during VC ramp up and down, VC threshold determined, and up high enough so that cannot remain on when VC is less than 4. Otherwise, depending on battery voltage, this may reverse conduct and load down the battery momentarily. Okay, interesting. A pin is provided on the 82C836 to protect the contents of the real-time clock and reduce power consumption whenever the system is powered down. The power grid pin should also be low whenever the system power supply is not within spec. Okay, well that's obviously the case. The pin must therefore active high. Okay, most AT-compatible architectures, the reset and power functionality is available separately on the 16 or 146818, and that is all combined into this chip. Another pin is provided to initialize the real-time clock whenever the system battery power is first applied. The PS MFP5, multifunction pin 5 pin, does not alter the CMOS RAM or clock counter contents, but it does initialize the necessary RTC control register bits. Deassertion of the PS disables generation of real-time clock interrupts and sets a flag indicating that the contents of the real-time clock may not be valid. A recommended circuit for controlling the PS input is also shown in figure 3.3. It's got to be this multifunction pin 5. This has got to be somehow related to our problem here. It's got to be. Multifunction pin, here we go, 5, bidirectional. Multifunction pin 5 is a bidirectional pin that has two functions. In internal RTC mode, the power sense input active high, indicating the state of the battery. The PS signal should be powered from the battery backup circuit. In external RTC mode, it's the real-time clock select active low. In external RTC mode, it's a decode of all I/O addresses. Okay, that seems unrelated. So I guess I don't fully understand what tells this chip, hey, run in super low power mode. The battery voltage should not be high enough to cause a net increase in backup voltage when normal power is turned off. Otherwise, the chipset and the oscillator will continue to be powered by the battery even when the power supply is turned on. Okay, yeah, that's fine. We don't have that problem. Battery drain will actually increase when power is on due to reverse conduction. That's not happening. We know that's not happening. Basically, that part of the circuit's perfect. I turned on the motherboard and immediately the draw from the battery is just gone. So it really feels like this chipset never switches into like the low power mode, and it just seems to keep running at full power, or maybe not full power, I don't know. And it doesn't say anywhere what, here what the actual power draw is of this chip while it's running in battery mode. But the odd thing is here, this is what's weird. Remember when I put that battery there, there was a ton of voltage drop across it, which doesn't make sense. Theoretically, if this is just sensing that signal, that shouldn't be happening. Oh, the battery died on this camera again. I was just testing that little resistor that I removed with hot air, and it is 100K. And this is the one I think is supplying that PS pin. So I'm just going to reinstall it onto the board and just measure the voltage at the multifunction pin on the chipset. All right, I found multifunction pin 5. It's right there. VCC, which goes to that cap, the bypass cap. It's 2 over, closer to the dot. Pin 1, basically. And sure enough, I restored some parts. So the tantalum cap is back on. I put that 100K resistor back on, so that is definitely 100K. So this 100K goes down here to this, I think it's a 10K, 102, yeah, 10K. And then on the other side of this 10K, there's this cap to ground. Well, that pin there is connected right here. If I move my hand so it focuses, it's connected absolutely to that multifunction pin 5. So that's that PS signal. And absolutely, that's exactly what this little circuit does. Now, the weird thing is when we turn this on, this is powered up. Yep, okay, it's running. Let's measure the voltage on the PS pin, because I think we're getting a lot of voltage drop. Well, we don't need to measure on there. We can just measure right here. Okay, we're getting 4.4 volts. So there's some voltage drop. If we start over here, 4.9, and then across 2.6. Well, that's interesting. I can't, it's so hard to see the traces. I can't exactly see how this is hooked up. So I guess, oh yeah, it goes through this diode here, which has 4.4 on one side. And on the other side, it's got 2.8. I don't know why. Obviously, this doesn't match the circuit exactly compared to what was in the data sheet. But I do know that this side of this little bypass cap here, this 4.5 volts, this is going to the chip. Oh, let's turn the chip back on. 4.7 volts now. And the power to the oscillator, 4.8. So that PS pin is seeing 4.7 volts right now. And the VCC to the chip is also 4.8. So I don't know. I don't fully get it. And of course, if we take a look at the battery, it's not getting charged because of the Schottky here. But the Schottky is blocking charging that would go to the battery otherwise. So we have 4.8 there. That's obviously coming from this power supply circuit. I guess these transistors probably. And there's the battery, 0.7, but that's fine. Schottkys leak when there's extremely low current, but the Schottkys do leak the reverse current. Anyways, but yeah, there's the 4.8, which makes its way to the oscillator, to the VCC on the main chip here. 4.8, and the PS pin, it's getting powered by this at 4.77. So that would be right over here. I don't want to short those pins with these probes. It just seems that this thing doesn't keep time. So I'm going to plug the bench power supply. I'm going to set it down to 3 volts. I'm going to plug it into here. There's currently no current draw on the power supply, and we'll turn this off. So the motherboard's off now. Let's check the voltage on that PS pin. Got to do it properly here. Look how twisted my leads are. So this is the PS pin. It's down at 2.6 volts. The power to the oscillator and the main chip, we're at 3 volts. And I don't see any excessive current draw right now, right? I'm looking at the power supply. It's all 0, 0, 0. It does show current draw once it ramps way up, but it's currently all at zeros. But I think I'm going to look in the data sheet here. Does this have anything about the voltages that this runs on? Maybe way at the end here. Oh, is this an A or a B? This chip is an A. Let's see what differences are. Fast video mode, not supported. Okay. It does not support hidden refresh. Okay. DRAM write operation, several different AC timing characteristics are noted. Well, I don't think any of that necessarily matters. Okay, standby supply current, 50 microamps with power good low. Standby refresh is disabled. VCC supply current, that's while the system is running, 140 milliamps. Looks like this can take 7 volts on VCC briefly. Supply voltage in standby. 3 volts minimum. Okay. I mean, that's got to be the problem right there, right? That's got to be the problem. that this chip, it just does not support running off a standard CR2032. That's got to be it. I'm gonna have to use 2. And we are right now at 3.0 because the power supply is at 3.2 volts. And I still don't have excessive current draw. I'm gonna raise it up to like 3.6, I guess. Now I'm checking the VCC into the chip, and we're at 3.4. And I'm gonna check the PS signal, 2.7. And I think what I need to do now is set this thing back into milliamp mode, and we're gonna have to monitor, I suppose. It's currently drawing 0.015 milliamps. So a very acceptable current draw. And I think I'm gonna have to do that thing where I go upstairs and clean up the kitchen a little bit, and I'll come back down. And maybe this was the problem the entire freaking time. And I think what that means is I need to get one of those battery holders, right? I don't actually have that can hold 2 of these in series, that is, and we'll get 6 volts out of it. And then I need to, I guess, put some of those diodes back in to drop the voltage down. So it's 5 volts. I don't know. It's just the thing is, earlier we had it drawing a bunch of current. Even when I had it at 3.6, 3.7 volts, it was still drawing current. So I still feel like something's wrong here. And I think we're just in a mode that, I don't know. I don't know what we're in right now. I think what I need to do actually is I'm going to turn this on, and we should set up the BIOS settings again. That way I know for sure if it fails, especially with the time, because we'll know if the time's not running for some reason. But yeah, by the way, with the system powered on, there's no current draw at all. It said 0. I assume it's not going to say the battery's dead right now because the PS signal is hooked back up again. Now that I put that resistor back in. Checks on bad. Okay, yeah, that's fine. All right. Okay, there's the time set. F10. It is late. I've been working on this for a very long time. And I'm going to cut the power. And on the multimeter, we're at 0.014 milliamps, so very low current. And I'm gonna let this run and we'll see what happens. Okay. All right, we're back. It's been, I don't know, at least 10 minutes or so. And this hasn't changed at all. It's just sitting here. And that was the problem the entire freaking time. So there's actually nothing wrong with this motherboard. It's just that if you try to use a CR2032, then it goes into a mode where it just starts drawing a whole ton of power and then drains your battery immediately. Which is kind of funny in a way. That means that when you do have whatever battery powering this motherboard, as the voltage drops, it's going to get to a point where all of a sudden the chipset sort of freaks out when it drops below that 3 volts, I guess, and then starts drawing a whole bunch of current and then drains your battery really quickly. It's fine if you have a rechargeable battery, not fine otherwise. Well, that was a lot of time to figure that out. And I must tell you that I have so many motherboards around the house, so many, stuff like this, and all of these I just power off a normal CR2032 and they're fine. So, like, I have not run into this particular issue. Even on this board, this one here, this is the other SCAT one. And does this use a clock chip? No. No, it doesn't. I'm pretty sure the battery, which I have a normal CR2032 on here, I think it just goes right into here and it's fine. There's no issue. I hadn't used this thing in ages and the battery is not dead on it. So this problem is sort of unique to either this chipset itself that's on here, the 3D6 one, or it's specific to the circuit design that's on the board, I suppose. Let's power it up, take a look at the CMOS settings, see if the clock, is still correct. And then I'm gonna have to try to figure out how to edit this together into some kind of usable video. I don't know if it's going to be possible or not. I really don't know if that's going to be possible. Oh, this is so funny. If I had just replaced it with another 3.6 volt battery, I would have been fine. Right. I guess what I still need to do is flash the BIOS chip. But yep, no error. And the time, perfect. That's exactly, it's 12:25 right now. So I can't even believe it. I can't even believe it. What a strange system that when the voltage gets slightly low, it just slams the battery with like 20 milliamps to just drain it down to zero. Like it just goes, no, you're done. You are done. And I suppose what that means is I need to order some of those dual battery holders that can hold 2 of these batteries and take the battery holder off the board that I added onto this. And then I need to put back some of those diodes I took off. I still have them stuck to this little piece of tape here, so I haven't lost them. Basically, I need to restore this motherboard back to the way it was. And then I'll put the little battery holder and I'll just have to stick it on the board somewhere. So when I do go to use this, and then I'll just take the little battery holder, those little plastic things, stick it on the board wherever. And with those dropper diodes, then the 6 volts will be fine. I think, you know, these can sometimes be 3.2 volts, which means you're going to get 6.4 volts. And I think the chipset doesn't appreciate getting the extra voltage. And the weird thing is, remember when I had it hooked up to the bench power supply and I had it at 4 volts and it was still drawing a ton of current? But I feel like the chipset was trying to run, like it wasn't in standby mode for some reason. And I'm wondering if it was that PS multifunction pin 5. I can't remember at the time if I had the resistor removed, that 100K resistor. And perhaps I did, or perhaps there was a bad connection and me resoldering it, re-adding that tantalum, re-adding the 100K kind of fixed whatever was going on there. I'm not really sure. And I really don't know also, by the way, what switch 2 does on there. I thought it was a CMOS clear setting, but that's clearly not the case because switching that doesn't seem to actually do anything. It seems to lower the voltage going to the chip. So maybe that's the point of it. I'm not sure. I'm trying to think here. If the original NiCad was installed, switch 1 would actually clear your CMOS because it would disconnect that battery entirely. You just turn the system off, let it wait 5-10 minutes or whatever, and it will be completely erased. But switch 2, I don't really know what that does. We could see that the VCC dropped from like 4.8 volts while the system was running down to like 4.4 or whatever, but what does that do? I don't know. And I think what I'm going to do right now is, before I go to bed, I'm just going to quickly remove the battery holder and the Schottky diode and stuff because there's no point to keep those on there. I'll probably reinstall the header for the battery, the external battery, since we'll just use that with the little battery pack of whatever type I end up using. And I'll try to reinstall those little regular diodes on the motherboard as well. I'll just restore the motherboard back to the way it was, basically. This was a whole lot of nothing, this video, wasn't it? A whole lot of nothing. And then in the morning, what I'll do is I will wake up and flash the BIOS from the AMI, and we'll see if we can control the multi-IO chip, because that's really the last thing that's wrong with this board. Otherwise, this thing completely works. Sweet. I wasted many hours. It was a learning experience, right? Okay, I'll see you in the morning. And we're back, it's the next day, and you wouldn't believe what I found last night when I was putting the motherboard back to stock. So here it is, and you may be noticing that I actually have a little battery pack plugged in. And I went into my little bin of parts and I found this dual 2032 holder I had made ages ago. Now here's the funny story. I was restoring this thing completely back to stock, so I removed, well, let me zoom in a little bit so we can see a little bit better of what I'm talking about. I removed the battery holder, I added that pin header back in, I reinstalled the 2 diodes, D3 and D4. And you might be noticing that D3, sorry that we're a little bit out of frame there, D3 looks a little bit different, and that's because the original diode that was there was so corroded I could not get it reinstalled. So I stole this diode off another scrap board, and you know, looking at this close up, these things are not crooked, but it doesn't matter. They are fully hooked up and working. So the positive voltage comes from the battery, it makes its way into that pin of D3, comes out there, it goes into this pin of D2, comes out there. That's 1.2 volts of diode drop, and it actually makes its way into this diode D1. That's another 1.2 volts, goes to that via through the switch, and then that makes its way over here to the clock chip and, you know, the main chipset VCC line. Now here's where things got funny, and I have some components here that are taped on. So what this one is the bad diode. That was the corroded one I couldn't reinstall, so I just saved it there. But what is this piece of tape, which I'm trying to peel off without shorting things out? All right, there we go. So what is this? That's a capacitor. And you'll notice that it's missing from C117. So as a refresher, I mean, for me, it's the next day, but you have just watched the first part of the video. Remember that the voltage that goes to VCC on the main chipset and to the clock chip or the oscillator there, it breaks off, it goes to R41, which then has a trace that goes to C117, that's a bypass cap to ground, but then there's another trace that makes its way to this diode, D5, down here, basically ends up right there and going to that via, and there's some stuff over here which I think supplies voltage, 5 volts, but from this via, this is what makes its way over to the multifunction pin 5 on the chipset. So remember, when I was powering the board from the bench power supply, I was measuring this 100K resistor and I was seeing all sorts of voltage drop. Anyways, this goes over to the multifunction pin 5. That's the PS pin that is required, as far as I'm aware, to let this chip know that it is running on battery power. Well, last night when I had restored this completely back to stock, which is how it is now, I hooked up this battery and it was measuring about 6.1 volts. I plugged it in and very quickly the voltage was dropping dramatically and it was all the way down to like 3 volts. And I was like, what is happening? So I hooked up the bench power supply and instead of the battery, because now it's easy, I can just clip right on to the terminals that I installed, the little external battery terminal, and I gave it 6.2 volts. And I looked at the power supply and it had like 60 milliamps of current draw at 6.2 volts. Well, that meant that the problem, which I thought was gone, had come back. Now, this is when I started probing around, and I'm sorry I didn't get this on camera, but it was like 1:30 in the morning and I just didn't feel like recording at that point. With the bench power supply, 6 volts going into the pin, I was noticing that there was a lot of voltage drop, and I mean a lot of voltage drop on the voltage pin to this and to the main chipset. But even more, checking this resistor on the side facing the dip switches here on the right side, we had the full voltage, well, the voltage after the diode drop from these diodes. So I was seeing like 4.4, 4.5 volts, something like that over on the right side. But on the left side, I was seeing 1 volt. So that 100K resistor had a whole bunch of voltage drop across it. And then that was carried through all the way over to here. And if you measure on this side, the right side of this resistor, that is the PS voltage going to the multifunction pin 5. So that meant that the voltage drop for the PS signal was happening right here. Well, this capacitor, which is this one right here, this is an MLCC multi-layer ceramic capacitor, and it's just bypass cap for this little part of the circuit, which was in the schematic when we looked at the data sheet for this. It had the little example circuit for the PS circuit, and it showed a 100K resistor and it showed a cap to ground. Well, on a whim, I measured the resistance of this capacitor with my multimeter, and you know, it's not perfect because obviously it's going to ground, it's, you know, there's other stuff there, but I was getting like 100K across this. That's not right. You should not get 100K across a capacitor. Now here's the thing, I thought, okay, well maybe it's something in parallel on this circuit, I don't know, somehow, but I was like, no, that can't be, because the only thing on the right side of the capacitor was this resistor, and the only thing on the left side was ground. So at the minimum, it should be whatever the resistance of this is plus this plus whatever else is on the circuit. I don't know. I should have seen more. Well, that led me to suspect that this freaking capacitor was the problem the entire time. Now, the funny thing is, MLCC caps, which I think is what this is, although maybe this is tantalum, people watching can probably chime in, but if it's MLCC, those typically break, and as far as I'm aware, I think they break open. So they kind of become out of circuit entirely, but maybe that's not the case. Maybe they go the other way. Whatever was happening, it seemed like this cap was causing this issue. So I removed it. And as soon as I measured with the multimeter, and we'll do that in a second, I was seeing like, meg ohm across those two pads. So with this installed, I was seeing 130K and it was sort of fluctuating all over the place. It was changing. With it out, I was seeing into meg ohm. Meg ohm is what I would expect to see across that capacitor. So I think what was happening is this capacitor is slightly shorted or leaky or something. And because of that, the 100K resistor here was bringing the 4 point whatever volts from this circuit to try to create the PS signal to go to the main chipset. Well, this cap kind of going short was causing severe voltage drop across this resistor R41, which resulted in the PS line becoming something like 1 volt, 1.2 volts, whatever, something very low. And then that has the side effect of telling this chip that it's not running on battery power. It thinks it's running on normal power, I guess, and it tries to power up. So that's my hypothesis, is when this voltage is a little bit lower than the VCC. So if this chip is getting, say, 4.5 volts VCC, you threw all of these caps around it, but the PS pin is at 4 volts, slightly lower, then it's gonna think, oh, I'm on battery power, so let me be ultra low power consumption, just keep the time, non-volatile RAM, but do nothing else. But when the PS voltage drops dramatically, this chip goes, oh, I guess I'm running on regular power. Let's power up and fully try to run. And I think that's what was happening. It's funny because the data sheet didn't really indicate exactly how that PS line works, like what the thresholds are. It just sort of had that example circuit and sort of was like, yeah, do this, so it knows it's on battery power, but it doesn't really say what it's going. I would kind of assume if the PS line was, I'm trying to think of the circumstances here. It's almost like, I don't know, because it doesn't quite make sense to me. I don't really fully understand it, but it just seems that the side effect of that PS line being really low voltage made the chip think that it was ready to run on full power. I don't know. It's the only thing I can come up with that I can explain the symptoms of what was happening. So what I did is I removed this capacitor from the board. Let me stick this down onto the bench here. I don't want to keep holding it. I removed it from the board. I connected the bench power supply and the current drain went away. We were back to, on the power supply, we just see all zeros. So I hooked this up so I could look at the milliamps, and yeah, it was like at 0.0 whatever, 15, the really low current draw we were seeing. So then I hooked up this battery pack, the one that's hooked up now. Everything seemed to be fine. The voltage on the pack was not dropping. It was staying pretty consistent. When I left last night, it was like around 6.1 volts. Now remember, I've abused these batteries and drained them like crazy, so I don't really know how good they are anymore. But I went into the CMOS setup and I set up the time and set some settings and whatever. And now the question is, it's been maybe 12 hours. Has the system been able to keep the time and keep the settings? Because that's the ultimate test. So what we should do now is I should check the voltage of the PS line and the voltage that's going to the chip, from the battery. Check that whole circuit. Make sure that it's still providing, it was like 4.7 volts, I think, last night when I went to bed on the VCC line, and the PS was a bit lower at 4.5 or something like that. Check those. Make sure the battery pack voltage itself is still decent as well. And then turn on the computer and see if the time has been maintained. And if it has, then I think I've pretty much figured out that this cap was 100% the problem the whole time, causing the chipset to go into like a full power mode, think it was regular power the motherboard up. That would immediately drain the battery. And I'll just go to a scrap board. I have some an old junk board right here. I'll just try to steal a cap off there to reinstall in the circuit just to make it complete again. Obviously that maybe helps fight some kind of like oscillation or whatever on that voltage rail. I don't know what it does exactly, but I can put it back and then the board is fixed. So let's do some measurements now. Now keep in mind, I have not powered this on since last night. It's been sitting here off the entire time, and hopefully it's still good. So let's get this going here. Okay, we're on DC volts. Every time I go to measure the DC volts, I use these pads, but this one and the one over here, which you can't see because it's behind the wire, they are a little bit corroded, so you don't make really good contact with them. So I like to use this one over here. Alrighty, first the voltage on the voltage pin going to the clock oscillator. 4.8. I think that's even higher than it was last night, and that's probably because the battery was being so abused. Let's check the battery voltage. I can just do it off this diode D3. 6.09. Okay, so it has dropped a slight amount. I'll just get a better connection. 6.09. Okay, batteries are not dead. And let's check the PS voltage, which is done off of this resistor here. 4.6. Yeah. So it looks like it's dropped just ever so slightly. Maybe the voltage on the clock circuit was a little bit higher. I can't remember, but I would expect this to drop a little bit just because this thing, this battery has been so abused, but it's still over 3 volts per cell, which means it's fine. It's totally fine. There's no reason to believe when we power this on that the clock's not going to be correct and the other settings are still going to be there. It's going to be fine. The freaking capacitor, which I have just lost, by the way. I thought I stuck it down. I didn't see where I stuck it. Okay, anyways, this is the, right here is the, what do you call it? It's the diode. Funny thing is, people watching the video will have seen where I put it and then seen where I moved it. All right, well, anyhow, let's turn this thing on and let's see if all of the CMOS settings have been retained, which I'm pretty positive they will all have been retained. Just, this, I don't think I've ever done such a difficult troubleshooting before in my life. Yeah, if this is really the problem, which I'm pretty sure this is exactly what the problem is, there we go. And also, I had said that I thought that the design of this motherboard meant if you used a 3-volt battery, it would go crazy and drain the battery. That's not the case. I think that cap was causing all of the issues. Control-Alt-S, 1239. All right, well, it is off by a little bit. It is 1246 right now. This is just after lunch. So we've lost a little bit of time. I did notice, though, I think this oscillator chip has a bad contact in the socket, and that's because the legs are all corroded. And look, I'm touching the chip, and the clock stopped. So yes, I think the problem is I need to sand the legs on this. Let's try to push it back in. Okay, I don't know what happened there. There we go. The time is going again. So I think that would probably explain the slight amount of time loss that we had there as the oscillator disappeared for the clock. So yeah, those legs are all corroded on that chip. So what I'll do is I'll use this little Dremel here just to polish the legs. I'll re-tin them and then stick them back in that socket, and that should fix that problem. So yeah, I mean, I'm pretty sure that that was the solution. That cap had gone bad, and it was causing that current draw to happen. And from my understanding, I don't think the current draw was coming from the cap itself because it was going through a 100K resistor. So you really can't draw that much current through a 100K resistor. So I think that PS line going to multifunction pin 5 on the chipset, when the voltage would drop because the cap was going short or leaky or whatever, that would cause the chipset to turn on and think that it was running full power. And that's what was draining the battery. So it was the chipset draining the battery, but because of that PS line having too low of a voltage, the voltage drop was too high on that line. Yeah, that's my explanation. I'm sticking to it. I think I finally zeroed in on exactly the problem. So next steps now, I'm going to sand the legs on the chip to fix that. I'm going to salvage a bypass cap off this board and stick it in place of the one I removed. And then I'll power everything up, make sure everything is working, and then we'll do the BIOS swap, and then I can finish out this video. All right, I've installed the new capacitor, I've sanded the legs, and I think everything is looking good. And I have the battery hooked up right now. So let's take a look at the PS voltage, which is right here. 4.7 or so, and we'll look at the voltage going to the chipset, 4.89, and that's coming from the battery. So that did the trick. This capacitor on the schematics was a 0.1 microfarad cap. This is on the example schematic at least. I installed a 0.08, so close enough. Should be fine. I think it just handles a little bit of prevents a bit of oscillation or whatnot. And I think we should be good with this. I tinned or sanded all the pins first with the Dremel, tinned the legs, and then I used some solder wick just to clean up any excess solder, and that plugged right into the socket without any issue. And I think we are good when it comes to issues for the power problem. Just absolutely wild that cap pulling that PS voltage down caused this issue. And while I was looking at the schematic for the value of this, I think I found exactly our problem. Take a look at this section in the datasheet. If power sensor MFP5 is low at any time, while power good is low, that's the signal that comes from the power supply that goes to 5 volts when all the rails have stabilized. Standby mode is cleared and the system reacts to power good exactly as described above, which probably is something to do with the system powering up and initializing. When using standby mode, the 82836 and PS must remain powered up even when power good is low. That's in standby mode, which is the ultra low power mode that runs from battery. In normal system operation, a battery will do this. In a test environment with no battery connected, a standby mode can be tested by driving power good low without actually turning the power off. I think that's the smoking gun right there. It's telling us that the PS line has to stay high while in standby. And if it goes low, the chipset goes into a mode that seems to be getting ready for operation of the entire system. It starts initializing the oscillators and doing all that kind of stuff, which obviously creates a big current drain on the battery. And that would never normally happen in operation because this PS line obviously is generated from the battery voltage, but when you turn on the power supply, I guess what happens is the power supply takes over VCC for the battery. It runs the oscillator and the chipset, and then the PS line doesn't matter anymore, and then the power good line becomes high once the rails stabilize, and then the chipset initializes. So I think my hunch about the chipset trying to initialize was right. And it was that bad cap pulling the PS line down to whatever, 1 volt or whatever, which by the time it got to the chipset, that was enough for it to think, okay, time to initialize. Someone switched on the power supply and I'm about to start to boot the system. But of course that wasn't happening and it would actually drain the battery. What that means actually is that my thought about the system not being able to run on a 3-volt battery might be incorrect. And even though we saw earlier that the minimum voltage in the datasheet for the chipset was 3 volts, it's quite possible in standby mode, even like 2 point whatever volts is enough to keep the clock running and the non-volatile RAM actually working. And that would explain why the other SCAT motherboard, the 286 motherboard I have, is still working fine with just a single CR2032. And it's been several months without any issue. It hasn't drained that battery. In addition to those mods, I also cut the pin off this IDE connector. That means that I can plug in the compact flash adapter. Which way does it go? Pin 1 is there, which, okay, it goes this way. So I can plug this in so we can actually test booting the system from this card. And I've gone ahead and I installed the ROM card into the system. So let's put the video card back in and we'll power the system on. And what I also did is I made a new EPROM using the AMI BIOS that was on the retro web. So I think we should be all good to go. I don't think we will have lost any of the CMOS settings or whatnot. So it's just funny, I'm just sitting here thinking, while I was making this video, I kept oscillating between, well, there was nothing wrong with the board. I was just giving it too low of a battery. And there was too much, there's something wrong with the board. I was kind of going back and forth. Well, there was something wrong with the board and it was that capacitor. And there it is, the system is freaking booting. Nice. Okay, so yep, internal IDE adapter absolutely does work. Speed 600, let's check our speeds. 21.84 megahertz and 3700 on the IDE. So our IDE on the VGA. So we are running at the 8 megahertz system bus speed right now, which is excellent. Very cool. All right, well, let's see. I need to stick this AMI BIOS in here. So we can see if we can then control the multi-IO, because that's really the missing component on this system. I'm gonna try to pull this out with this chip lifter. Can I get this out? Oh yeah, there we go, came out. All right, it should be a 27512. That's what I prepared with this chip. The notch is away from me. Let's make sure I plug this in the right way. Okay, there it is. All right, here we go, fingers crossed. It's gonna post. There are post codes. Oh, yes, excellent, excellent. Ah, right. That's a slow memory count, isn't it, though? AMI, it does say SCAT 3.04 down at the bottom. Checksum failure, of course, because what's stored in the non-volatile RAM is going to be completely different for this BIOS. Oh, nice. All right. Auto configuration with BIOS defaults. So I think we're going to have standard AMI stuff here. So the time is correct. That's interesting. So that's shared between the two BIOSes. Hard drive types, whatnot, keyboard, disabled, enabled. Okay, here we go. Above 1 megabyte memory test. That's cool. So you can actually disable on this one. We can turn the parity check on or off. We'll just turn that off. It's not really needed. System boot, numlock, processor checks, floppy seek, boot speed, CPU boot speed. I wonder if it allows us to adjust the multiplier on the CPU like the other BIOS does. Fast gate 820. There was no option in the other one for that. Turbo switch function. Some of this stuff I didn't see on the other one. Oh, this has more adapter shadow ROM stuff. Well, that's really cool. I don't remember where my XT-IDE ROM is. I think it's at D. Let's just shadow all of that space there. That will speed up the XT-IDE dramatically. And then it does the 64K for the system ROM, and then it does the VGA BIOS as well. So this is a better BIOS than the other one. Here we go, advanced. Oh yes, you can control this stuff here. Look at that. So it was my hunch about them releasing this board and having just the regular BIOS that wasn't designed for this multi-IO chip, and there was no way to control it. And then they added the control with this. So let's leave it on disabled, and let's see if we can actually disable it, because it should not boot now from the compact flash card. Low CPU clock speed. So is this the non-turbo speed? You can control the non-turbo speed, which I suppose is that same setting we saw in the other BIOS, but it didn't tell us that it was the low speed. Very interesting. So with this, that means taking out the turbo jumper, or actually rather installing it, results in half the CPU speed. But you could do a quarter speed or an eighth speed. And then the bus clock speed, this is what we had on the other one. So we have the same settings. We'll do /4. And then the DMA, I don't know, I'll just leave it. Refresh interval, we have that. Coprocessor ready. Okay, I don't know. Additional RAM wait states, we're turning that off. We don't need that. CAS extended wait state, I don't know. Let's turn this stuff off. RAS timeout, there's a bunch more stuff in here that wasn't in the other one. Extended boundary, that was there. That has to do with the EMS, which we don't want. Okay, let's try this. And what it should not boot off the XT-IDE right now. The ROM is going to be there, but it shouldn't see anything. Yeah, it freaking works. This BIOS can control the multi-IO, and the other one couldn't. What garbage? What absolute garbage? So let's go turn the IDE back on. Oh, wow. I can't believe they would release a motherboard with a BIOS that had no control over like the additional I/O ports. Doesn't that seem wild? So we can turn on the IDE controller like that. What we can do as well is once this boots up, I'll put a turbo jumper on. I just have to find my jumpers. Ah, here they are. And we will see if the IDE is working now. We'll see if it's really /8, because that's what I have it set to. Now I have all the wait states, yep, there we go, it worked anyways. I have all the wait states turned off, so this should be as fast as possible right now. Let's see if there's any actual difference. Okay, no, it's just that 21. So the thing is, this BIOS, it has obviously special customization specific for this chipset. So that means if you have a motherboard with this exact chipset, it's probably gonna work. The thing is, it's also customized for the multi-IO chip. And if you have a motherboard that doesn't have that, I don't know what will happen. Maybe nothing. Let's put the turbo jumper on. Just getting this jumper Making sure it's the right thing, and it should drop by 1/8. Okay, that's not the right, that's a different jumper spacing. Okay, here we go. Try again. 1/8. Yes, that freaking worked. You can totally control the non-turbo clock speed on this thing. That's frankly cool. F9 for retest. So 60 megahertz, we should be at what, 4? No, 2 megahertz. Oh, this is cool. This is a pretty cool feature. I haven't seen this. I haven't really, yeah, 2.7 megahertz. And we pull the jumper off, and it goes right back. And I think this jumper here turns off the wait state thing. So that slows it down. And now if we put the turbo jumper on, it's gonna slow down so dramatically. It's like a 2 megahertz IBM PC-AT. So this is way slower than the original IBM 5170. Pretty cool. And in the service manual or the tech manual for the chipset, it tells you how to alter the registers to change that clock speed. It is possible you could change the non-turbo clock speed on the fly from DOS, which would mean this is a very flexible motherboard. If you're trying to run really old, slow software like XT software, should work on this motherboard because you just have to have a turbo switch and then alter that turbo speed to suit your needs. And yeah, freaking awesome. So I think that's really it for this video. It's gonna be a really, really long one. I loaded the footage I have so far on this video into my editor, and there was like 5.5 hours. I'm obviously gonna edit that down. I can't put out a video that's 5.5 hours, but some people have been asking for a long form video. I think this is gonna be a long form video. It's gonna be a good test. It's gonna be a second channel video, but it will be a good test to see if people are interested in seeing that. Incidentally, I will absolutely, here's the ROM. I'll upload the dumped ROM up to RetroWeb, and I'll take pictures of this motherboard as well. And those will be up there. So there'll be some high-res pics of the front and the back of this older revision of the board, although it seems to be identical to that other version anyways. But yeah, if you enjoyed this absolutely insane long video, thumbs up. If you didn't, you know what to do. I still can't believe it was the capacitor that was causing all these issues, but now I fully understand why. I didn't go through all the effort to fully reverse engineer that circuit, but I guess I did enough of it that I'm able to figure out how things work. And it took me quite a long time to get there, but it just sort of shows that the time investment required for doing these types of fixes can be dramatic. And I thought this was going to be a really quick video on the second channel of this motherboard. Well, turned out that that's not the case. And I need to finish this up, get this edited, and I need to work on another main channel video because, you know, doing 2 videos a week, it takes quite a bit of my time, especially when I've worked on this particular video for so many hours. And now, to be honest, I got to edit it up because I know people are like, why don't you do it without editing? Well, I make mistakes talking, and when you know you have a camera recording the footage, you make mistakes talking, and you ended up editing that stuff out just because you say the same thing 5 times. And if I left that in, it would be hilarious. If I'm doing a live stream, obviously, I don't know, your mind knows that you don't have the ability to go edit the video afterwards. And maybe that's the trick. Maybe I just need to do a live stream trying to repair one of these motherboards. But then who's going to watch that for 5.5 hours? I don't know, maybe people would. I guess if you're here watching this video at this point and you would like to see me try to live stream one of these, I suppose let me know. I could certainly try it. I don't know. That would just be, that's something I'm not used to doing because obviously I don't typically do that. I edit my videos, so I'm just not used to it. Anyway, okay, I got to wrap this up. I hope you enjoyed this long video. If you did, thumbs up, subscribe. Thanks to my supporters. Their names are going up here. You can become a supporter too. That really helps me out. YouTube ad revenue is just in the toilet. It really, I mean, it's not like there's no money from it, but it's just, it's now not even, it's a small fraction of the amount of income I have now. Most of my income all comes from supporters. And so when I say that I wouldn't be able to do this without them, I'm not kidding. The YouTube ad revenue, it would be a struggle for me to just survive on at this point. And that's really because I don't do video sponsors and I don't have mid-roll ads on my videos. I don't know if you see them or not, but I don't have that feature turned on. And that, according to YouTube, cuts my revenue generation down dramatically. Obviously, YouTube Premium is a highly recommended thing you get. It takes away all your ads from YouTube, and it actually pays supporters like me more. I can see my revenue breakdown, and I get more money from people who have Premium than I do from ad buys. I think because a lot of people have ad blockers, and therefore it doesn't pay that well because a lot of the ads don't get shown. And the YouTube Premium, obviously, there's no ad blocking or whatever, and even though you don't see ads, there's a cut of the money from the premium that goes to the creators. So yeah, that strangely enough, YouTube Premium really does benefit the creators more. And when people use ad blockers, I mean, I would too. It's really annoying, those ads. But Premium costs, I don't know, whatever it costs. I have an old grandfather plan, but say it's $12, $13 a month. If you watch a lot of YouTube, it's worth it. You get a music subscription to use YouTube Music, which I personally do use as well. It's not the best, but I used to use Spotify. I used to use other services, and they're all the same. They have their pros and cons, and the YouTube one, while not great, it's included, and that I can't complain about that. So anyhow, okay, I'm gonna stop babbling. Thank you very much for watching. I hope you liked this video, and that's gonna be that. So stay healthy, stay safe. I'll see you next time. Bye. All right, stop.